Subscribe to the channel so you don't miss out on any of these videos. Imagine a place where light, something that we think of as the fastest, most unstoppable force in the universe, is trapped. A region where photons, the very particles of light, are caught in an endless loop, unable to escape, unable to move forward. It sounds like something out of a science fiction story, but it's real. This phenomenon is called the photon sphere, and it exists near one of the most mysterious and awe-inspiring objects in the universe, a black hole. The photon sphere is where light doesn't travel in straight lines anymore. Instead, it dances, orbits, and sometimes vanishes into the abyss. This is the story of how gravity bends the very fabric of reality, trapping even light in its grasp. But how does this happen? What is the photon sphere really? And what does it tell us about the bizarre and fascinating nature of black holes? To understand the photon sphere, we first need to think about gravity in a way that might feel unfamiliar. Gravity isn't just a force that pulls objects together, it's a distortion in the fabric of space and time itself. Imagine placing a heavy ball on a stretched-out sheet of rubber. The ball creates a dip, and if you roll a smaller ball near the dip, it spirals toward the larger one. That's a crude way of visualizing what gravity does in space. Now, imagine something so massive, so dense, that it creates a hole in the fabric so deep that even light, which usually zips past everything, gets caught in its curve. That's what happens near a black hole, and the photon sphere is the point where the bending of spacetime becomes so extreme that light particles start to orbit the black hole like planets orbit a star. But this isn't an orbit like you might imagine. It's not stable. It's chaotic and fragile. If a photon, a particle of light, wanders slightly too close to the black hole, it gets sucked in and never escapes. If it strays just a little too far, it breaks free and zips off into the vastness of space. The photon sphere is like a razor-thin boundary, a cosmic tightrope where light walks a perilous path. And here's where things get even stranger. Unlike the smooth orbits of planets around the sun, the paths that photons take around a black hole aren't circular. They're warped, twisted by the intense gravity, forming strange, looping patterns that defy easy description. What's even more fascinating is how this affects what we can see. If you were somehow able to safely hover near a black hole and look toward the photon sphere, you wouldn't just see the area directly around it. You'd see light from stars and galaxies that have bent around the black hole, creating a distorted, almost funhouse mirror view of the universe. In fact, the photon sphere is one of the reasons why black holes often appear surrounded by a glowing ring in artists' renderings and images like the famous one captured by the Event Horizon telescope. That glowing ring, known as the black hole's shadow, is partly defined by the photon sphere. It's the last place light can orbit before either escaping or being swallowed forever. But the photon sphere isn't just a visual curiosity. It's a key to understanding the fundamental nature of black holes and the extreme physics that govern them. For one thing, the photon sphere tells us just how strong a black hole's gravity is. The closer the photon sphere is to the black hole, the more intense the gravitational pull. In a non-rotating black hole, the photon sphere forms at a radius of about 1.5 times the Schwarzschild radius, the so-called event horizon, beyond which nothing can escape. For rotating black holes, the situation is even more complicated. The photon sphere gets distorted and shifts depending on the speed and direction of the black hole's spin, creating a phenomenon known as frame dragging, where spacetime itself is twisted like a whirlpool. This twisting of spacetime adds another layer of complexity to the photon sphere. For light particles traveling in the same direction as the black hole's spin, the photon sphere is closer to the event horizon. For light moving against the spin, the photon sphere is farther out. This creates an asymmetric, warped region that challenges our understanding of motion, time, and causality. Scientists study these effects to test Einstein's theory of general relativity, which predicts much of what we know about how black holes warp space and time. So far, the observations match the predictions, but the photon sphere remains an area of active research, where new discoveries could reshape what we know about the universe. One of the most mind-bending aspects of the photon sphere is what it implies about the behavior of time near a black hole. As you approach the photon sphere, time itself begins to slow down relative to an observer far away. This effect, known as gravitational time dilation, means that if you somehow manage to hover just outside the photon sphere, you would experience time much more slowly than someone farther away from the black hole. A few minutes near the photon sphere could correspond to hours, days, or even years in the outside universe. This isn't just a theoretical idea, it's been observed in less extreme environments, like near neutron stars, which are also incredibly dense but not quite black holes. The photon sphere also raises profound questions about the nature of reality itself. What does it mean for light to be trapped in an orbit? Is it really trapped? Or is it following a path that's determined by the geometry of spacetime? And if light, the fastest thing in the universe, can be caught in this way, what does that say about the limits of our understanding? These questions aren't just academic. They're at the heart of some of the biggest mysteries in physics, from the nature of gravity to the possibility of unifying general relativity with quantum mechanics. The photon sphere represents one of the strangest and most extreme aspects of the universe's gravitational landscape. To truly appreciate its significance, we need to dive deeper into how it interacts with the cosmos and the mind-bending scenarios it creates. For instance, imagine the idea of being able to see the back of your own head, not through a mirror, but because light from you could orbit around the black hole and return to its point of origin. This is theoretically possible within the photon sphere. However, the conditions to achieve this are so specific and unstable that even the slightest disturbance would break the orbit and send the light in a completely different direction. This hypothetical self-viewing scenario is a direct consequence of how black holes warp spacetime. The intense gravitational field bends light so much that it forms closed loops. If you were situated at the photon sphere, somehow safe from the lethal radiation and tidal forces, you would witness a distorted version of the universe, filled with strange mirages and warped images of stars, galaxies, and other celestial objects. You would essentially be looking at a kaleidoscope created by gravity, where light from multiple directions is bent into the same point, overlapping and intertwining in ways that defy normal perception. One of the most intriguing aspects of the photon sphere is its role in gravitational lensing. Black holes are natural lenses, bending light around them and magnifying objects behind them. The photon sphere amplifies this effect to an extreme degree. In gravitational lensing, light from a distant source passes near a massive object, like a galaxy or black hole, and gets bent around it. But when light comes near the photon sphere, it doesn't just bend, it can circle the black hole multiple times before escaping. This creates multiple, stacked images of the same object. If you were observing a star positioned directly behind a black hole, you might see several ghost images of that star, each one slightly offset and distorted. This phenomenon is one of the ways scientists confirm the existence of black holes and study their properties. Another fascinating implication of the photon sphere is how it reveals the connection between light and time. Light traveling through the photon sphere has essentially been delayed by the black hole's gravity. If a photon orbits the black hole several times before escaping, it carries with it a record of the black hole's history during that time. In a way, the photon sphere acts as a kind of time capsule, storing information about the black hole's environment and the events that occurred nearby. Scientists theorize that studying the light escaping from the photon sphere could provide insights into the black hole's behavior, including changes in its spin, the movement of nearby matter, and even the violent mergers of black holes or neutron stars. This brings us to one of the most pressing questions in modern physics. Can we use the photon sphere to decode the secrets of black holes? Black holes are notoriously enigmatic, shrouded by the event horizon, which prevents any information from escaping. But the photon sphere lies just outside this barrier, making it one of the last places where we can directly observe the effects of a black hole's gravity. By analyzing the light that escapes from the photon sphere, researchers hope to uncover clues about the internal structure of black holes, the distribution of matter and energy near the event horizon, and even the elusive singularity at the black hole's core. The photon sphere is also crucial in understanding the dynamics of accretion disks, the swirling disks of gas and dust that often surround black holes. These disks are among the brightest objects in the universe, emitting intense radiation as matter falls toward the event horizon. Some of this radiation interacts with the photon sphere, creating complex patterns of light that reveal the structure and motion of the accretion disk. By studying these patterns, astronomers can measure the spin of the black hole, the composition of the accretion disk, and the strength of the magnetic fields that drive powerful jets of particles away from the black hole. But the photon sphere isn't just a tool for studying black holes, it's also a testing ground for the laws of physics themselves. General relativity, Einstein's groundbreaking theory of gravity, predicts the existence and behavior of the photon sphere with remarkable accuracy. However, there are still open questions about how general relativity interacts with quantum mechanics, the theory that governs the behavior of particles on the smallest scales. The photon sphere exists at the intersection of these two realms, where gravity is incredibly strong, and quantum effects may become significant. By probing the photon sphere, scientists hope to uncover evidence of new physics that could bridge the gap between these two fundamental theories. This exploration is not just theoretical. Observatories like the Event Horizon Telescope, EHT, are already pushing the boundaries of what we can observe near black holes. The first ever image of a black hole's shadow, captured by the EHT in 2019, provided a glimpse into the photon sphere and the region surrounding it. The shadow itself is larger than the event horizon due to the bending of light and the photon sphere. Future observations with even more powerful telescopes could reveal the intricate details of how light behaves in this extreme environment, offering a closer look at one of the universe's most mysterious phenomena. As we delve deeper into the mysteries of the photon sphere, we are confronted with profound philosophical questions about the nature of reality. What does it mean for light to be trapped? Is the photon sphere a boundary, or is it a pathway, a place where light and information take on a new form? And what does it say about the universe that such a place exists, where the rules we take for granted are bent and broken by the sheer power of gravity? The photon sphere challenges our understanding of the universe in ways that are both humbling and exhilarating. It reminds us that the cosmos is far stranger and more complex than we can imagine, filled with phenomena that stretch the limits of our knowledge and our imagination. As we continue to study this enigmatic region, we may not only uncover the secrets of black holes but also gain a deeper appreciation for the intricate and beautiful fabric of the universe itself. The photon sphere, as fascinating and intricate as it is, also serves as a playground for extreme physics. One of the most thrilling aspects of this region is how it tests the very limits of light's behavior. Normally, light travels in straight lines unless acted upon by some external force, like gravity. In our everyday experiences, light bends only slightly, such as when it passes through water or glass. But near a black hole, light's journey becomes chaotic and unpredictable. The photon sphere is the threshold where this chaos takes on a new dimension, pushing light into orbits that seem more like the choreography of a cosmic ballet. Within this sphere, light experiences gravitational redshift to an extreme degree. Gravitational redshift is a phenomenon where light loses energy and shifts to longer wavelengths as it escapes a strong gravitational field. The closer light is to the photon sphere, the more energy it must expend to break free from the black hole's pull. Some photons lose so much energy that they never escape, instead remaining trapped in this peculiar limbo. The light that does escape carries a signature of the black hole's gravitational force, effectively giving us a glimpse into one of the most extreme environments in the universe. But the photon sphere isn't merely a theoretical construct or a mathematical curiosity. Its existence has practical implications for how we study the cosmos. Black holes, despite their fearsome reputation, are relatively small on cosmic scales. This makes them difficult to observe directly, even with the most advanced telescopes. The photon sphere, however, magnifies the black hole's presence, creating a visual shadow that scientists can detect. This shadow, surrounded by the glowing halo of the accretion disk, is one of the key features astronomers use to identify black holes and study their properties. One of the most striking features of the photon sphere is its instability. Unlike stable orbits, such as those of planets around a star, the orbits within the photon sphere are precarious. Any slight disturbance, whether from an incoming particle, A shift in the black hole's spin, or even the interference of another photon, can disrupt the orbit, sending the light spiraling inward toward the event horizon or outward into space. This instability means that while photons can theoretically orbit the black hole indefinitely, in practice, they rarely do. Instead, they become part of the ever-changing dance of light and gravity that defines the photon sphere. This instability also highlights an important distinction between the photon sphere and the event horizon. While the event horizon represents a point of no return, where nothing, not even light, can escape the black hole's pull, the photon sphere is a boundary zone, teetering on the edge of escape. It is a place where the rules of physics seem to balance on a knife's edge, creating conditions that are as mesmerizing as they are fleeting. One of the key factors that influence the photon sphere's behavior is the black hole's spin, or angular momentum. Black holes come in two main varieties: non-rotating, Schwarzschild, black holes, and rotating, Kerr, black holes. In a non-rotating black hole, the photon sphere is a relatively simple, spherical shell surrounding the event horizon. But in a rotating black hole, the situation becomes much more complex. The spin of the black hole distorts spacetime, dragging it along in a phenomenon known as frame dragging. This distortion causes the photon sphere to warp and shift, creating asymmetries that affect how light behaves. In a rotating black hole, the photon sphere can have different radii depending on the direction of the light's orbit. Photons orbiting in the same direction as the black hole's spin experience a smaller photon sphere, while those orbiting in the opposite direction encounter a larger one. This asymmetry adds another layer of complexity to the already intricate dynamics of the photon sphere, making it a rich area of study for physicists and astronomers alike. The interaction between the photon sphere and the accretion disk is another area of active research. Accretion disks are composed of matter, gas, dust, and other particles that spirals toward the black hole, heating up and emitting intense radiation as it does so. Some of this radiation interacts with the photon sphere, creating a dazzling display of light and energy. The interplay between the accretion disk and the photon sphere not only contributes to the black hole's overall luminosity but also provides valuable data about its spin, mass, and other characteristics. The photon sphere's role in gravitational lensing is another critical area of study. Gravitational lensing occurs when a massive object, like a black hole, bends the light from a distant source around it. The photon sphere amplifies this effect, creating multiple images of the same source. These images are not just visually stunning but also scientifically invaluable. By analyzing the patterns of light bent by the photon sphere, astronomers can glean insights into the black hole's mass, spin, and even the distribution of matter in its vicinity. But the photon sphere isn't just a passive participant in these cosmic phenomena. It actively shapes the environment around the black hole, influencing the behavior of nearby matter and energy. For instance, the photon sphere plays a crucial role in the formation of relativistic jets, powerful streams of particles that are ejected from the poles of some black holes. These jets are among the most energetic phenomena in the universe, capable of extending for thousands of light years and impacting the evolution of entire galaxies. The photon sphere contributes to the formation of these jets by funneling energy and angular momentum from the accretion disk to the black hole's poles. The photon sphere also has implications for the search for new physics. While general relativity provides a robust framework for understanding the photon sphere, there are still many unanswered questions about how it interacts with quantum mechanics. The extreme conditions near the photon sphere, where gravity is incredibly strong and spacetime is highly curved, make it an ideal testing ground for theories that attempt to unify these two pillars of modern physics. Some researchers speculate that studying the photon sphere could provide evidence of quantum gravity, a theoretical framework that seeks to describe gravity at the smallest scales. As we continue to explore the mysteries of the photon sphere, we are reminded of the profound interconnectedness of the universe. The photon sphere is not just a feature of black holes, it is a window into the fundamental nature of reality. It challenges our understanding of light, gravity, and space-time, forcing us to confront questions that lie at the very heart of physics and cosmology. The journey to understand the photon sphere is far from over. With advancements in technology, such as next-generation telescopes and space-based observatories, we are poised to uncover even more about this enigmatic region. Each discovery brings us closer to understanding the universe's most extreme and fascinating phenomena, opening new doors to the mysteries of black holes and the cosmos as a whole. The photon sphere, as enigmatic as it is, also serves as a portal to the broader mysteries of black holes and spacetime itself. It challenges our fundamental understanding of light and gravity while teasing the boundaries of observable reality. To fully grasp the photon sphere's role in the cosmic landscape, we must dive deeper into its interactions with spacetime distortions, its observational potential, and its philosophical implications for our understanding of the universe. One of the most compelling aspects of the photon sphere is how it represents the interplay between light and curved spacetime. Light, as we know, is a constant in the universe, traveling at an unvarying speed in a vacuum. However, in the presence of intense gravitational fields, light is subject to bending, warping, and even confinement. The photon sphere epitomizes this phenomenon, where spacetime curvature is so extreme that light is trapped in a relentless dance around the black hole. Imagine photons whizzing around the black hole at nearly inconceivable speeds, locked in an intricate web of gravitational forces. Each photon is in a delicate equilibrium, constantly trying to escape the black hole's pull but finding itself redirected by the warped fabric of spacetime. This perpetual struggle between motion and confinement creates the photon sphere's unique dynamic. It's a place of relentless motion, a chaotic symphony of light navigating the razor-thin boundary between freedom and inevitable collapse into the event horizon. The photon sphere's intricate structure also allows us to explore time dilation to an extraordinary degree. Time dilation, a concept rooted in Einstein's theory of general relativity, becomes extreme near a black hole. For an observer far away, time appears to slow down for anything nearing the photon sphere. This means that events occurring within this region are perceived as unfolding at a sluggish pace. Conversely, for the photons within the sphere, the universe outside the black hole appears to speed up dramatically. This relativistic effect underscores how profoundly the photon sphere alters the perception of time and space. Observationally, the photon sphere offers one of the most tantalizing clues to understanding black holes. Its presence amplifies the gravitational lensing effect, creating phenomena like Einstein rings and multiple images of background objects. These visual distortions provide astronomers with a natural laboratory to test the predictions of general relativity. By analyzing the light patterns and lensing effects near the photon sphere, scientists can gather data on a black hole's mass, spin, and even its angular momentum. A groundbreaking milestone in observing the photon sphere was achieved with the Event Horizon Telescope, EHT, which captured the first-ever image of a black hole's shadow in 2019. This shadow, surrounded by a glowing ring of light, is partly a result of the photon sphere's behavior. The photons trapped in the sphere contribute to the glowing halo, while the black hole's event horizon casts the shadow. This historic image not only confirmed the existence of black holes but also validated many of the theoretical predictions about the photon sphere. Interestingly, the photon sphere's properties also play a critical role in the formation of quasi-stable structures like photon rings. These rings are produced when light makes multiple passes around the black hole before escaping to an observer. Each subsequent ring represents photons that have orbited the black hole one more time than the previous ring. These structures provide a layered view of the black hole's gravitational influence, and could help refine measurements of its parameters with unprecedented precision. The photon sphere's influence extends beyond black holes themselves, affecting the environments around them. For instance, the interaction between the photon sphere and the accretion disk creates unique patterns of radiation. The intense gravitational field distorts the accretion disk's light, producing relativistic beaming and Doppler shifts. These effects cause the disk to appear brighter and more compact from certain perspectives, adding to the black hole's visual complexity. Moreover, the photon sphere might hold clues to one of the universe's most perplexing questions: the nature of dark matter. Some theories propose that black holes, and by extension their photon spheres, could act as cosmic detectors for dark matter interactions. If dark matter particles exist near a black hole, their behavior could influence the photon sphere's dynamics. Detecting subtle anomalies in the photon sphere's structure or behavior might provide indirect evidence for dark matter, opening a new frontier in astrophysics. The philosophical implications of the photon sphere are equally profound. It is a region where our intuitive understanding of reality begins to break down. In the photon sphere, the separation between light and darkness blurs, challenging our perception of what it means for something to be visible. The photons trapped in this region exist in a state of limbo, neither escaping into the universe nor succumbing to the event horizon. This ambiguity forces us to reconsider the nature of observation itself. What does it mean to see something when the very act of observation is dictated by the curvature of spacetime? The photon sphere also invites questions about the fundamental nature of light. Light, as a carrier of information, is instrumental in our understanding of the universe. Yet in the photon sphere, light becomes both the messenger and the prisoner, locked in a gravitational struggle that reveals the extreme limits of physics. This paradox highlights the interconnectedness of light and gravity, two forces that shape our universe in ways we are only beginning to comprehend. Technologically, the photon sphere presents unique challenges and opportunities. Observing such a distant and extreme region requires instruments capable of detecting minute variations in light and gravitational signals. Innovations in interferometry, high-resolution imaging, and space-based telescopes are paving the way for more detailed observations of photon spheres in the future. These advancements promise to unlock new insights into the behavior of light and gravity under the most extreme conditions. Theoretical physicists are also delving deeper into the photon sphere's mysteries, exploring its potential to reveal new physics. Some researchers propose that the photon sphere could be a testing ground for theories of quantum gravity, string theory, or even extra dimensions. The extreme curvature of spacetime near the photon sphere might amplify subtle quantum effects, providing a unique environment to observe phenomena that are otherwise undetectable. As we push the boundaries of our understanding, the photon sphere remains a symbol of both the known and the unknown. It embodies the delicate balance between light and darkness, order and chaos, observation and mystery. Each photon that orbits the black hole carries with it a story of the universe's most extreme conditions, a narrative written in the language of light and gravity. In the grand tapestry of the cosmos, the photon sphere is a thread that connects us to the very fabric of space-time. It is a reminder of the universe's complexity and beauty, a testament to the power of curiosity and discovery. As we continue to explore this enigmatic region, we are not just learning about black holes and photons. We are uncovering the fundamental truths of existence itself. The photon sphere's significance extends far beyond its physical characteristics. It opens the door to profound philosophical and existential questions about the nature of reality, perception, and even humanity's place in the universe. As light becomes trapped in an eternal dance, either fully escaping nor entirely consumed by the black hole, it represents a cosmic metaphor for balance and paradox. This region encapsulates the idea that boundaries in the universe are not always clear-cut, challenging the binary distinctions humans often rely on to understand their environment. The photon sphere highlights the dual nature of light itself. While we often consider light as the ultimate messenger, a vehicle carrying information across the vast expanses of space, the photon sphere traps this messenger in a paradoxical state of motion and stasis. It is as though the universe, through the photon sphere, creates a natural archive of photons, locking their stories in perpetual orbit around a black hole. But this archive is inaccessible, beyond reach, teasing us with the knowledge that vast amounts of information exist in the universe, yet remain eternally out of grasp. This realization ties into a broader philosophical quandary. What does it mean to know something? For much of human history, we have relied on light, whether in the form of visible light, radio waves, or other parts of the electromagnetic spectrum, as a medium for understanding the universe. Yet in the photon sphere, light loses its ability to deliver information in a straightforward manner. It becomes enigmatic, a symbol of knowledge that exists but cannot be shared. This disconnect forces us to confront the limitations of human perception and understanding. If light, the very essence of observation, can be confined and distorted, then how much of the universe is hidden from us by the nature of its own rules? Beyond philosophy, the photon sphere also has implications for understanding the potential interconnectedness of cosmic events. For example, black holes and their surrounding photon spheres act as gravitational anchors in the universe, influencing the motion of nearby stars, gas clouds, and even galaxies. The photon sphere, as an intermediary zone, plays a subtle yet critical role in how these massive objects interact with their environments. By studying it, scientists can gain insights into how energy and matter behave in the most extreme conditions, potentially offering clues about the formation of galaxies and the evolution of cosmic structures. Another fascinating aspect of the photon sphere lies in its role as a cosmic theater of relativistic effects. Light, when trapped in the photon sphere, undergoes extreme gravitational redshifting and blue shifting, depending on its motion relative to an observer. These shifts can alter the wavelength of light to the point where it transitions across the electromagnetic spectrum, from visible light to infrared, or even X-rays. This dynamic interplay of shifting wavelengths provides scientists with a unique opportunity to study the behavior of light under conditions that cannot be replicated on Earth. This behavior also has practical implications for observational astronomy. Instruments designed to detect and analyze light near photon spheres must account for the complex distortions caused by extreme gravitational lensing. The photons escaping the photon sphere are not just warped, they are often magnified, duplicated, or smeared into intricate patterns. These patterns contain valuable data about the black hole's properties, such as its spin rate and orientation relative to Earth. As technology advances, future telescopes may be able to parse these intricate details, offering even deeper insights into the photon sphere and the black holes it surrounds. Interestingly, the photon sphere also interacts with other phenomena associated with black holes, such as relativistic jets. These jets, composed of charged particles accelerated to near-light speeds, often originate from the regions just outside the event horizon. The photon sphere can influence the trajectory and intensity of these jets, adding another layer of complexity to their study. By examining the relationship between the photon sphere and relativistic jets, scientists hope to unravel the mechanisms driving these powerful cosmic outflows, which can extend thousands of light-years across space. In the broader context of the universe, the photon sphere serves as a reminder of the interconnectedness of cosmic scales. While it exists on the minuscule scale of individual photons orbiting a black hole, its effects ripple outwards, influencing structures on galactic and even intergalactic levels. This duality, being both incredibly small and immensely impactful, mirrors the nature of many phenomena in the universe, where the micro and macro are intricately linked. Moreover, the photon sphere has a unique role in speculative physics, particularly in discussions surrounding the information paradox and the nature of black hole interiors. Some theories suggest that the photon sphere might act as a kind of observational boundary, capturing certain properties of matter and energy as they approach the event horizon. If true, this could have profound implications for the study of black hole entropy and the possible resolution of the information paradox, a key puzzle in modern physics that questions whether information falling into a black hole is lost forever. The photon sphere's extreme environment also offers a natural laboratory for testing theories of quantum gravity. At the intersection of quantum mechanics and general relativity, quantum gravity seeks to explain how gravity operates at the smallest scales. The photon sphere, with its intense curvature of spacetime, could amplify quantum effects, making them observable in ways that would otherwise be impossible. Detecting such effects would not only validate aspects of quantum gravity theories, but also provide a deeper understanding of the universe's fundamental forces. As we advance our understanding of the photon sphere, it also deepens our appreciation for the interconnectedness of scientific disciplines. The study of this enigmatic region requires contributions from astrophysics, mathematics, computer science, and even philosophy. It is a testament to the collaborative nature of human inquiry, where insights from diverse fields come together to illuminate the mysteries of the cosmos. The photon sphere, in all its complexity and mystery, stands as a beacon for the curious mind. It challenges our perceptions, stretches the limits of our understanding, and inspires us to look deeper into the fabric of the universe. As light dances endlessly in this gravitational cauldron, it tells a story not just of black holes but of the unyielding human desire to explore, understand, and marvel at the cosmos. The photon sphere serves as a profound symbol of humanity's quest for understanding, reminding us of the paradoxes and enigmas that lie at the heart of the cosmos. Its existence challenges the intuitive ways in which we comprehend the universe, where light, something we perceive as synonymous with knowledge and observation, is rendered powerless to escape. This peculiar dance of photons, caught in an eternal loop, underscores the intricate and sometimes counterintuitive nature of physical laws. One fascinating implication of the photon sphere is its role in challenging the concept of linearity in space and time. Photons trapped in this region do not follow the straightforward paths we typically associate with the motion of light. Instead, they loop endlessly, bound by the curvature of spacetime. This raises intriguing questions about the experience of time for these photons. While humans experience time as a linear progression, the motion of photons in the photon sphere suggests that time, under extreme gravitational influence, can become a loop. If a photon could somehow observe its own journey, it would perpetually encounter the same point in space, creating a kind of temporal stasis. This notion of looping time brings us closer to the tantalizing idea of closed time-like curves, theoretical constructs in general relativity where time loops back on itself. While the photon sphere is not a closed time-like curve in the strictest sense, its behavior hints at the possibility of such phenomena existing under the right conditions. This opens the door to wild speculation about the nature of time travel, causality, and the limits of what is physically possible in the universe. The photon sphere also forces us to reevaluate the concept of observation in the context of black holes. In traditional physics, observation involves detecting light or electromagnetic radiation emitted or reflected by an object. However, in the photon sphere, light neither escapes nor remains stationary, it is trapped in perpetual motion. This makes direct observation of the photon sphere exceedingly difficult. Astronomers must rely on indirect evidence, such as the gravitational lensing effects produced by light near this region, to infer its existence and properties. These gravitational lensing effects are not just a tool for studying the photon sphere but also a gateway to understanding the broader structure of black holes. Light bent around the photon sphere creates a series of distorted, magnified, and sometimes overlapping images of background objects. These distortions, known as Einstein rings or arcs, provide a wealth of information about the mass, spin, and orientation of the black hole causing them. By analyzing these phenomena, scientists can reconstruct a detailed picture of the black hole and its surroundings, even when the black hole itself remains invisible. One of the most visually striking aspects of the photon sphere is the way it contributes to the appearance of black holes in visual simulations. When we see depictions of black holes, such as those created for movies like Interstellar or real-life images captured by the Event Horizon Telescope, the photon sphere plays a crucial role. It creates the glowing, halo-like structure often associated with black holes, as light from surrounding matter is bent and focused into complex, dynamic patterns. These visualizations help bridge the gap between abstract theoretical concepts and tangible representations, making the enigmatic nature of the photon sphere more accessible to the public. As humanity's tools for exploring the universe improve, the study of the photon sphere will likely yield even more surprises. Advanced telescopes, like the next-generation Event Horizon Telescope or space-based observatories, could provide unprecedented views of the light trapped near black holes. These observations could refine our understanding of not only the photon sphere but also the interplay between black holes and their environments. Furthermore, the photon sphere may hold clues to one of the most profound mysteries in modern physics: the reconciliation of general relativity and quantum mechanics. Black holes, as regions of extreme gravitational curvature, are natural laboratories for studying quantum effects in curved spacetime. The photon sphere, as an interface between the observable universe and the event horizon, could reveal how quantum processes operate under such conditions. For example, the interaction of photons within the photon sphere might exhibit quantum entanglement, or other non-classical behaviors, offering glimpses into the elusive theory of quantum gravity. The study of the photon sphere also underscores the importance of interdisciplinary collaboration in science. Astrophysicists, mathematicians, computer scientists, and philosophers all contribute to the exploration of this enigmatic region. Advanced simulations, grounded in mathematical models of general relativity, are essential for visualizing the behavior of photons in such extreme environments. Meanwhile, philosophical discussions about the nature of observation, causality, and information enrich our understanding of the broader implications of the photon sphere. Another compelling avenue of research involves the potential role of photon spheres in the detection of primordial black holes, hypothetical black holes formed in the early universe. These black holes, much smaller than their stellar or supermassive counterparts, could still possess photon spheres if their mass is sufficient. Detecting and studying these primordial photon spheres could provide insights into the conditions of the early universe, the formation of cosmic structures, and even the mysterious nature of dark matter. The photon sphere also invites speculation about its role in hypothetical advanced technologies, such as those envisioned in science fiction. For instance, could the unique properties of light near the photon sphere be harnessed for advanced imaging techniques or even as a means of storing information? While such ideas remain speculative, they highlight the potential practical applications of understanding extreme physical phenomena. Moreover, the photon sphere offers a poignant reminder of the limits of human comprehension. As light orbits endlessly in this gravitational dance, it embodies the idea that some aspects of the universe are fundamentally unknowable. While science continually pushes the boundaries of understanding, the photon sphere stands as a testament to the enduring mystery of the cosmos, a mystery that inspires awe, curiosity, and a deep sense of wonder. In contemplating the photon sphere, we are reminded of the intricate beauty of the universe and the interconnectedness of all its components. From the smallest particle to the largest cosmic structure, everything is governed by the same fundamental laws, yet those laws manifest in ways that are endlessly varied and often surprising. The photon sphere is not just a feature of black holes. It is a window into the deeper truths of existence, a microcosm of the paradoxes and marvels that define the cosmos. The photon sphere is not merely a boundary around black holes, it is an intricate interplay of light and gravity, a region that embodies the delicate balance between escape and entrapment. This region provides a striking contrast between the predictable and the chaotic, a place where light, the fastest thing in the universe, is rendered captive. This paradox challenges our intuitive understanding of motion, freedom, and the fundamental nature of light itself. Imagine photons, the very particles of light that carry information across the cosmos, being bound in perpetual orbits. It's an extraordinary concept, given that light is typically associated with unbridled motion, racing across space at 186,000 miles per second. Yet, within the photon sphere, these photons are forced into a cosmic ballet, tracing circular paths determined by the immense gravitational pull of the black hole. This peculiar behavior redefines what we know about light and its interactions with spacetime. The size and shape of the photon sphere are not uniform. They depend on the mass and spin of the black hole. For non-rotating, or Schwarzschild black holes, the photon sphere is a perfect sphere, existing at a radius 1.5 times the Schwarzschild radius, which is the event horizon. However, when a black hole is spinning, as described by the Curvature, the photon sphere becomes distorted, with its geometry influenced by the black hole's angular momentum. In this case, the photon sphere isn't a singular entity but rather a series of photon trajectories that differ depending on their direction relative to the black hole's spin. The study of these photon trajectories reveals profound truths about spacetime. In the case of rotating black holes, frame dragging, a phenomenon predicted by Einstein's general relativity, plays a critical role. The black hole's spin drags spacetime around with it, causing photons that orbit in the same direction as the spin to follow different paths compared to those orbiting against it. This creates a fascinating asymmetry in the photon sphere, with prograde, forward-moving, and retrograde, backward-moving, orbits existing at different radii. The effects of the photon sphere extend far beyond its immediate vicinity. The gravitational lensing caused by light bending near the photon sphere leads to some of the most spectacular phenomena observable in the universe. When light from a distant star or galaxy passes near a black hole, the intense gravity bends the light into arcs, rings, or even multiple images of the same object. These effects are not only visually stunning but also scientifically invaluable, providing astronomers with a powerful tool for studying black holes and the large-scale structure of the universe. Gravitational lensing around the photon sphere can also produce an eerie phenomenon known as relativistic images. These are faint, distorted repetitions of background objects, created as light circles the black hole multiple times before escaping toward the observer. The more times the light orbits the black hole, the fainter and more compressed these images become, creating an almost fractal-like pattern of increasingly subtle features. Observing these relativistic images would require extraordinary precision and sensitivity, but their detection could open up new frontiers in astrophysics. The photon sphere is also crucial in understanding the so-called shadow of a black hole. When light from the accretion disk, a swirling ring of matter spiraling into the black hole, is bent by the photon sphere, it creates a dark silhouette against the bright background. This shadow, first imaged by the Event Horizon Telescope in 2019 for the supermassive black hole at the center of the galaxy M87, is a direct manifestation of the photon sphere's influence. The size and shape of the shadow provide insights into the black hole's mass, spin, and even potential deviations from general relativity. In addition to its observational significance, the photon sphere has profound implications for theoretical physics. It represents a natural boundary where classical and quantum descriptions of reality might intersect. For example, the behavior of photons in the photon sphere could reveal quantum effects that are amplified by the extreme curvature of spacetime. These effects might include quantum entanglement between photons or even the creation of virtual particles due to the intense gravitational field. One of the most tantalizing questions involves the role of the photon sphere in black hole thermodynamics. Black holes are not just regions of intense gravity, they are also governed by laws analogous to the laws of thermodynamics, with properties such as entropy and temperature. The photon sphere, as the outermost region where light interacts with the black hole's gravity, could play a role in how energy and information are transferred across the black hole's boundaries. Understanding this interaction might offer clues to resolving the black hole information paradox, one of the most profound unsolved problems in modern physics. The photon sphere also serves as a reminder of the interconnectedness of the universe. The photons trapped in this region are not isolated entities. They are part of a larger cosmic tapestry, influenced by the black hole, the surrounding environment, and even distant stars and galaxies. This interconnectedness underscores the idea that no phenomenon in the universe exists in isolation. Every particle, every photon, and every force is part of a grand, unified system governed by the same underlying principles. In a sense, the photon sphere is a microcosm of the universe itself, a place where the familiar and the mysterious converge. It challenges our understanding of fundamental concepts like motion, observation, and causality, while also inspiring new questions about the nature of reality. What does it mean for light, the ultimate messenger of information, to be trapped in a never-ending cycle? How does this phenomenon reflect the deeper truths about the universe and our place within it? As we continue to explore the cosmos, the photon sphere will remain a focal point of curiosity and discovery. Its study requires not only advanced technology and theoretical insight but also a sense of wonder and imagination. For in the photon sphere, we glimpse the profound beauty and complexity of a universe that is both familiar and unfathomably strange, a universe that beckons us to keep asking questions, to keep seeking answers, and to keep reaching for the light. The photon sphere's enigmatic nature reveals yet another layer of complexity when we consider its relationship to time. Time, as we know, behaves differently near massive objects, stretching and distorting under the influence of gravity. Near the photon sphere, this time dilation becomes extreme. An observer far away would perceive time near the photon sphere to crawl almost to a standstill, as if the photons themselves are frozen in their relentless orbits. For anything attempting to traverse this region, time would pass normally relative to its frame of reference, but the perception from afar paints a surreal picture of slowed existence. This temporal distortion holds immense theoretical importance. It hints at the profound connection between space and time, a relationship that Einstein's theory of general relativity so elegantly describes. The photon sphere, as a dynamic boundary, showcases how intertwined these concepts are, offering a living experiment of spacetime curvature. If we were to send a probe to the edge of the photon sphere, its onboard clock would tick at a vastly different rate compared to a clock on Earth. Such experiments, though currently beyond our technological reach, could validate the extreme predictions of relativity and deepen our understanding of the cosmos. Additionally, the photon sphere challenges our concept of observation. Light carries information, allowing us to see and interpret the universe. However, in the photon sphere, photons neither escape nor converge entirely. They are locked in a gravitational embrace. This peculiar behavior creates a paradox of visibility. What would one see if somehow situated within the photon sphere? The photons around you would never leave the black hole, yet they would continue their orbit. In such a scenario, you might witness distorted versions of your surroundings, stretched and warped by the relentless curvature of spacetime. Interestingly, this thought experiment raises deeper questions about the limits of perception and knowledge. If photons are forever trapped, unable to carry information beyond the photon sphere, does this create an intrinsic boundary to what can be observed or known about the black hole? These are not just theoretical musings. They strike at the core of what it means to understand the universe. The photon sphere symbolizes the frontier between the knowable and the unknowable, a tantalizing edge where human curiosity meets the limits of comprehension. The physics governing the photon sphere also has implications for how energy is redistributed in the vicinity of black holes. Matter that falls toward a black hole often forms an accretion disk, a swirling mass of high-energy particles that emits immense radiation. The photon sphere influences how this radiation escapes, bending light into complex patterns that depend on the black hole's properties. This creates a shimmering halo of light around the black hole, which is not only visually stunning but also scientifically significant. The light carries information about the black hole's mass, spin, and even the nature of the infalling material. This halo, often referred to as the Einstein ring, when viewed as a perfect circle, is a direct consequence of the gravitational lensing caused by the photon sphere. The precise shape and intensity of this ring depend on numerous factors, including the observer's location and the properties of the black hole. Scientists can analyze these patterns to extract valuable data, essentially using the photon sphere as a natural laboratory for studying extreme physics. The photon sphere also plays a role in astrophysical phenomena like quasars, which are among the brightest objects in the universe. Quasars are powered by supermassive black holes at the centers of galaxies, where matter spirals into accretion disks and emits staggering amounts of energy. The photon sphere in these systems affects how light is emitted and distributed, contributing to the complex and variable brightness of quasars. Understanding these dynamics helps astronomers study the evolution of galaxies and the role black holes play in shaping the cosmos. Beyond its astrophysical significance, the photon sphere inspires philosophical and metaphysical reflections. It embodies the concept of boundaries, both literal and metaphorical. It is a region where light, the ultimate symbol of clarity and understanding, is confined. This evokes questions about the limits of knowledge and the nature of reality itself. Is the photon sphere a barrier that forever separates us from the truth of what lies within a black hole? Or is it a bridge, a region where the rules of the universe are laid bare in their most extreme and fascinating form? These questions are not merely abstract. They resonate deeply with our human drive to explore and understand. The photon sphere serves as a reminder that the universe is a place of endless wonder and mystery, where every answer leads to new questions. It challenges us to think beyond our limitations, to imagine the unimaginable, and to embrace the complexity of existence. From a practical perspective, studying the photon sphere has the potential to revolutionize our understanding of the universe. Advances in technology, such as more sensitive telescopes and innovative observational techniques, are bringing us closer to unraveling its secrets. Projects like the Event Horizon Telescope, which captured the first image of a black hole's shadow, are paving the way for future discoveries. These endeavors are not just about pushing the boundaries of science, they are about redefining our place in the cosmos. The photon sphere also has implications for future space exploration. Understanding the extreme environments near black holes could inform the design of spacecraft capable of withstanding intense gravitational forces. Such knowledge might one day enable missions to explore the outskirts of black holes, bringing us closer to the edge of the unknown. The photon sphere, in this context, is not just a theoretical construct but a real-world challenge and opportunity for humanity's quest to reach the stars. Ultimately, the photon sphere is a testament to the beauty and complexity of the universe. It is a place where light dances with gravity, where time and space are twisted into shapes that defy intuition, and where the mysteries of existence are laid bare for those who dare to look. It reminds us that the cosmos is not just a collection of objects and forces but a living, dynamic system that continues to surprise and inspire. The photon sphere is more than a scientific curiosity. It is a symbol of the human spirit. It represents our unyielding desire to understand, to explore, and to push beyond the boundaries of what is known. As we peer into the depths of the photon sphere, we are not just studying the universe, we are discovering ourselves. The photon sphere also brings into focus one of the most fundamental questions in modern physics: the interplay between quantum mechanics and general relativity. Black holes, and by extension, their photon spheres, are the ultimate testing grounds for these two great pillars of science. On the one hand, general relativity describes the large-scale structure of spacetime and the gravitational forces at play. On the other hand, quantum mechanics governs the behavior of particles at the smallest scales. The photon sphere exists at the intersection of these domains, making it a fascinating but challenging environment to study. The photons within the sphere are influenced by quantum effects, as well as the curvature of spacetime. This raises questions about how quantum particles behave in such an extreme gravitational setting. Do photons experience quantum fluctuations as they orbit? Could quantum mechanics offer insights into the stability of the photon sphere? These are open questions, and answering them could provide clues about the elusive theory of quantum gravity, a framework that unifies quantum mechanics and general relativity. One particularly intriguing aspect of the photon sphere is its potential connection to Hawking radiation, the theoretical process by which black holes emit energy. While Hawking radiation originates from the event horizon rather than the photon sphere, the two are intrinsically linked through the geometry of the black hole. The photon sphere represents a region where gravitational and quantum effects are closely intertwined. Studying it could deepen our understanding of how black holes lose mass over time and eventually evaporate, a process that challenges our understanding of entropy and the conservation of information in the universe. The role of the photon sphere in gravitational wave research is another area of active investigation. When two black holes merge, they create ripples in spacetime known as gravitational waves. These waves carry information about the properties of the black holes, including their mass, spin, and orbit. The photon sphere contributes to the dynamics of these mergers, influencing how energy is radiated during the process. Observing these effects through detectors like LIGO and Virgo provides indirect evidence of the photon sphere's existence and its role in shaping the universe. From a computational perspective, modeling the photon sphere is an immense challenge. Simulating the behavior of photons in such an environment requires solving Einstein's field equations under highly specific conditions. These equations describe how matter and energy influence the curvature of spacetime, but their complexity grows exponentially near a black hole. Advanced techniques, such as numerical relativity and machine learning algorithms, are being developed to handle these calculations. By improving our ability to simulate the photon sphere, scientists can make more accurate predictions and design better observational strategies. In addition to its scientific implications, the photon sphere has captivated the imagination of the public and artists alike. Its eerie beauty and mysterious nature make it a popular subject in science fiction, where it often represents the boundary between the known and the unknown. Films, books, and video games have depicted the photon sphere as a place of intrigue and danger, a cosmic riddle that challenges both the characters and the audience. These depictions, while fictional, reflect the deep fascination humanity has with the unknown and the extreme. The philosophical implications of the photon sphere cannot be overstated. It challenges our understanding of causality, observation, and the nature of reality. If photons can be trapped in perpetual orbit, does this mean that information about the past is eternally preserved in some form? Could the photon sphere serve as a cosmic archive, holding the light of events long since forgotten? These ideas stretch the boundaries of conventional thought, inviting us to rethink what we know about time and space. The photon sphere also serves as a metaphor for human curiosity. Just as photons are trapped by the gravity of the black hole, our thoughts and questions are drawn toward the unknown. The photon sphere reminds us that there are limits to what we can observe and understand, but it also inspires us to push those limits. It is a place where the laws of physics are tested to their extremes, a reminder that the universe is far more complex and mysterious than we can imagine. In the future, technological advancements may allow us to study the photon sphere in even greater detail. Space-based telescopes with enhanced sensitivity could capture more precise images of black holes, revealing the intricate patterns of light shaped by the photon sphere. Interferometry techniques, which combine data from multiple telescopes, could provide higher resolution and open new windows into the study of black holes. These developments could transform our understanding of the photon sphere and its role in the cosmos. There is also the possibility of using the photon sphere as a natural laboratory for testing exotic theories of physics. For example, some theories suggest that black holes could harbor hair, or unique features that distinguish them beyond their mass, charge, and spin. The photon sphere could reveal subtle deviations from classical predictions, offering evidence for new physics. Similarly, alternative models of gravity, such as string theory or loop quantum gravity, could predict different behaviors for the photon sphere, providing a way to test these ideas against observational data. The photon sphere's impact extends beyond black holes. Its principles can be applied to other celestial phenomena, such as neutron stars and white dwarfs, which also exhibit strong gravitational fields. By studying these objects, scientists can gain insights into the broader behavior of light and matter in extreme environments. The photon sphere, in this context, is not only a crucial feature of black holes but a concept that resonates throughout astrophysics, allowing us to understand the intricacies of gravity's influence on light and matter across the universe. One of the more exciting avenues for future research involves using the photon sphere as a tool for understanding the universe's most extreme environments. As astronomers develop increasingly advanced technologies, such as the next generation of space telescopes and gravitational wave detectors, the ability to observe black holes and other compact objects will be greatly enhanced. With these tools, researchers can gather more data on the behavior of light near the photon sphere, expanding our knowledge of how these objects warp spacetime and shape the universe around them. For example, future missions could capture more detailed images of black hole accretion disks and observe how photons are bent, stretched, and trapped in the intense gravitational well. This could lead to better models of how matter behaves near black holes, shedding light on the mechanisms that power quasars, gamma-ray bursts, and other high-energy phenomena. The photon sphere plays a pivotal role in the energy dynamics around black holes, and understanding this process is essential for unraveling the broader astrophysical context in which these events occur. Furthermore, the study of the photon sphere could have practical implications beyond the realm of theoretical physics and astronomy. By exploring the extreme conditions around black holes, scientists could gain insights into how similar forces might manifest in other areas of physics. For example, understanding how photons behave in such a strong gravitational field could offer new perspectives on light-matter interactions in general. This could eventually lead to new technologies or materials that harness these insights, potentially affecting fields like telecommunications, energy, and quantum computing. The photon sphere's role in gravitational lensing, as mentioned earlier, is also of paramount importance. Gravitational lensing occurs when light from distant objects, such as stars or galaxies, passes near a massive object like a black hole. The intense gravitational field of the black hole bends the light, magnifying and distorting the image of the distant object. The photon sphere plays a crucial role in this process, as light rays passing close to the event horizon are bent at extreme angles. This phenomenon has already provided astronomers with a wealth of information about the universe's structure and distribution of mass. Gravitational lensing can also be used to detect exoplanets, study the dark matter distribution in galaxy clusters, and even probe the mysteries of dark energy. By studying how light behaves around the photon sphere, scientists can refine their models of the universe's large-scale structure and the hidden forces that govern its evolution. These observations can help scientists test fundamental theories about the nature of gravity and the behavior of light in the most extreme conditions. In addition to gravitational lensing, the photon sphere offers another method for testing the limits of our understanding of physics: studying the shadow of a black hole. The Event Horizon Telescope's groundbreaking imaging of the supermassive black hole in M87 revealed the iconic shadow that is cast by the black hole's event horizon. The edge of this shadow is influenced by the photon sphere, which contributes to the way light is bent and shaped as it orbits the black hole. The detailed study of these shadows could provide valuable insights into the black hole's mass, spin, and the properties of spacetime near the event horizon. The process by which photons orbit in the photon sphere also links back to the concept of gravitational capture, a phenomenon that occurs when light or other particles are captured by a black hole's gravity. This idea is critical when studying the behavior of light in extreme gravitational fields, especially when considering phenomena such as Hawking radiation. If we could better understand how light behaves at the photon sphere, we might make progress in understanding how black holes interact with their environment, shedding light on some of the most fundamental questions in cosmology and particle physics. On a more conceptual level, the photon sphere is a reminder of the universe's vast complexity. It exists in a region where the normal rules of physics seem to break down or behave in ways that are difficult to predict. Light, the most ubiquitous form of energy in the universe, is completely transformed in this extreme environment. Photons, which typically travel in straight lines through space, are forced to bend and follow the curvature of spacetime, effectively becoming prisoners of the black hole's gravity. This realization invites us to reflect on the limitations of our own understanding. Despite all of our advances in science and technology, there are still places in the universe where our knowledge is incomplete or where current theories break down. The photon sphere, as a mysterious and still relatively unexplored aspect of black holes, represents the frontier of human knowledge. It pushes the boundaries of what we know about light, gravity, and the very fabric of spacetime, offering a window into the most extreme and unknown regions of the cosmos. As we continue to explore the cosmos, we will undoubtedly encounter more mysteries like the photon sphere, phenomena that challenge our understanding and force us to rethink the fundamental laws of nature. The study of these enigmatic regions will not only improve our understanding of black holes and other celestial objects, but will also provide new tools and insights for exploring the broader universe. In the grand scheme of things, the photon sphere might be just one of many strange and mysterious phenomena scattered across the cosmos, but its significance is undeniable. It serves as both a scientific puzzle and a philosophical reflection on the nature of reality. As we continue to probe the depths of space, we will uncover more secrets about the universe and perhaps find ourselves standing on the precipice of new discoveries that could transform our understanding of existence itself. With each discovery, we get one step closer to unlocking the mysteries of the universe, and the photon sphere will likely remain a critical part of that journey, an elusive, captivating feature of black holes that holds secrets waiting to be uncovered. As our understanding of the photon sphere deepens, so does the potential for new and exciting discoveries that could reshape our view of the cosmos. But the path ahead is not easy. Our observations of these extreme phenomena rely heavily on indirect evidence, simulations, and sophisticated models. The sheer complexity of black holes and the regions surrounding them means that no single experiment or observation will be enough to fully comprehend the photon sphere's role in the universe. One promising avenue for studying the photon sphere is through advancements in observational technologies. In the near future, the development of more powerful telescopes could allow scientists to observe black holes and their photon spheres with unprecedented clarity. The James Webb Space Telescope, for instance, is poised to capture high-resolution images of distant galaxies and their central black holes. While Webb may not be able to directly observe the photon sphere itself, the data it collects will help researchers refine their understanding of the space surrounding black holes, including the accretion disks and photon orbits that play such a pivotal role. Additionally, space missions that employ advanced gravitational wave detectors, such as LIGO and Virgo, have already begun to offer incredible insights into the behavior of black holes and neutron stars. These detectors are sensitive to the ripples in spacetime that are produced by massive objects, including the mergers of black holes. The detailed analysis of gravitational wave signals has already provided indirect evidence of black hole mergers, allowing scientists to infer information about the masses, spins, and orientations of the black holes involved. As detection methods continue to improve, these tools will allow us to study the interactions between photons, spacetime, and gravity near the photon sphere in even more detail. One of the next frontiers in this research is to develop simulations that accurately model the behavior of light near the photon sphere. These simulations will help scientists predict how photons interact with the curved spacetime around black holes. Such models would be invaluable for interpreting data from new observations and could lead to more precise measurements of black hole properties. In particular, simulations of light and matter in the photon sphere will help us understand the conditions that lead to phenomena like gravitational lensing and the creation of black hole shadows. As the precision of our observations improves, it may also be possible to detect more subtle effects caused by the photon sphere. For instance, scientists are now investigating how the photon sphere might influence the polarization of light that escapes the vicinity of a black hole. Polarization is a property of light that describes the orientation of its electromagnetic waves. By studying the polarization of light around black holes, scientists can gain further insights into the environment surrounding these objects and the role that the photon sphere plays in shaping the light that we observe. Beyond the physical understanding of the photon sphere, there are also philosophical and conceptual questions that it raises. The very existence of the photon sphere challenges our understanding of the relationship between light and gravity. Photons, the fundamental particles of light, are massless, and according to general relativity, they should follow the curvature of spacetime. However, in the photon sphere, this curving becomes so extreme that even light itself is trapped in perpetual orbit. This creates a paradox. Light, which is typically free to travel across vast distances, becomes a prisoner of the black hole's gravity. In some sense, the photon sphere represents a boundary where the laws of physics, as we know them, seem to break down, forcing us to confront the limits of our understanding. One particularly thought-provoking idea is the question of what happens to the information carried by photons that are trapped within the photon sphere. According to the principles of quantum mechanics, information cannot be destroyed, but at the same time, it is unclear how this principle operates near the event horizon of a black hole. The debate surrounding the information paradox remains unresolved, and the photon sphere is central to this discussion. If photons are trapped in an orbit around the black hole, does that mean that the information they carry is preserved forever, or could it be lost as the black hole evaporates through Hawking radiation? This issue continues to drive debates in theoretical physics, and the photon sphere may hold crucial clues to its resolution. Another area where the photon sphere has captured the imagination is in the realm of science fiction. The concept of light becoming trapped in orbit around a black hole is a fascinating narrative tool that has appeared in various books, movies, and television shows. In these fictional depictions, the photon sphere is often portrayed as a place of mystery and danger, where space and time are distorted to such an extent that the usual rules of reality no longer apply. While these representations are, of course, speculative, they do reflect the deep intrigue that the photon sphere generates. For many, the photon sphere serves as a symbol of the unknown, a reminder of how much there is yet to learn about the universe. Beyond fiction, the photon sphere also has real-world applications in technology and research. As we continue to develop more sophisticated space telescopes and gravitational wave detectors, our understanding of black holes and their photon spheres will provide new opportunities for advancing our scientific knowledge. The data collected from these instruments will not only deepen our understanding of the most extreme objects in the universe but will also improve our ability to measure and interpret cosmic phenomena. For instance, by studying how photons behave in the photon sphere, we can learn more about the fundamental properties of spacetime itself. Moreover, the photon sphere could play a role in unlocking new frontiers in quantum mechanics. As physicists continue to probe the relationship between general relativity and quantum theory, the photon sphere may provide a key to understanding how these two frameworks interact. The behavior of light near the photon sphere is influenced by both the geometry of spacetime and the quantum properties of light, creating a unique laboratory for testing the limits of our theories. By studying these effects, scientists hope to uncover new insights into the nature of quantum gravity, a theory that seeks to reconcile the differences between the two. The photon sphere is an enigmatic and crucial feature of black holes that continues to captivate scientists and the public alike. As we gain more advanced observational tools and develop better theoretical models, we will undoubtedly uncover even more about this mysterious region of space. The photon sphere challenges our understanding of light, gravity, and spacetime, and it holds the potential to unlock some of the deepest mysteries of the universe. Whether through the lens of astrophysics, quantum mechanics, or philosophy, the photon sphere remains an important subject of study, one that reminds us how much we still have to learn about the universe and the fundamental forces that govern it. As our exploration of the photon sphere continues, we begin to realize that it represents more than just a physical phenomenon. It serves as a window into the deeper workings of the cosmos, a realm where space, time, and light are woven together in ways that defy our conventional understanding. The photon sphere lies at the very edge of one of the most powerful forces in nature, gravity, and it provides us with an opportunity to study how this force shapes everything around it, from the smallest particles to the largest celestial bodies. The intricacies of the photon sphere go beyond simple orbits of light. The study of this region challenges our perceptions of the relationship between mass, energy, and the fabric of spacetime itself. While we've discussed the theoretical aspects of the photon sphere, it's important to dive deeper into its practical implications for scientific research, as well as the ongoing debates it sparks in the scientific community. One of the most fascinating aspects of the photon sphere is its potential to reveal new insights into the behavior of light in extreme environments. We've already mentioned the role that gravitational lensing plays in bending light around black holes. This bending of light not only alters the appearance of distant objects, but also allows us to peer into regions of space that would otherwise be obscured. When light passes near the photon sphere, it is affected by the curvature of spacetime, creating optical illusions and strange distortions. These phenomena can help us study the properties of black holes, which would otherwise be invisible. Astronomers and astrophysicists have been able to use gravitational lensing to detect distant galaxies and quasars that are located behind black holes, or to uncover objects that might otherwise be hidden behind cosmic clouds of gas and dust. By analyzing how light interacts with the photon sphere, scientists can use this data to measure the mass and size of a black hole, as well as its spin and charge. These measurements help refine our understanding of the types of black holes that exist in the universe and how they influence the surrounding space. As we dive deeper into the gravitational effects surrounding black holes, we also encounter the phenomenon of time dilation. As light approaches the photon sphere, the gravitational pull of the black hole slows down the passage of time for that photon, relative to an observer at a safe distance. This effect becomes even more pronounced as the photon gets closer to the event horizon, where time appears to almost freeze. These relativistic effects have been confirmed by observing time dilation in the behavior of particles near massive objects, and they further illustrate how the fabric of spacetime warps in the presence of extreme gravity. Time dilation near the photon sphere has profound implications for our understanding of the flow of time itself. It challenges the notion that time is an absolute, unchanging constant and suggests that time is relative, influenced by the intensity of gravity. This understanding of time as a flexible concept, rather than a fixed one, opens the door to new ways of thinking about the universe. It could help us understand phenomena such as the passage of time in black hole environments, and the ultimate fate of information that falls into them. Another area where the photon sphere holds promise is in the study of the accretion disk surrounding a black hole. The accretion disk is a swirling mass of gas, dust, and other matter that is slowly drawn toward the black hole by its immense gravity. As this material spirals inwards, it heats up due to friction, emitting intense radiation. The behavior of light as it interacts with the accretion disk is closely tied to the photon sphere, and studying these interactions could provide new insights into the complex physics of black holes. The photon sphere's influence on light is a crucial factor in understanding the mechanics of accretion disks. Light that is emitted by the disk can be bent and distorted as it passes near the photon sphere. Some of this light may even become trapped in orbit, forming part of the photon sphere's vast, glowing halo. This effect could allow scientists to better study the inner workings of black holes and their accretion disks by observing the patterns of light that escape from them. Additionally, the study of the photon sphere provides a crucial testbed for theories of quantum gravity, which seeks to unify general relativity and quantum mechanics. These two pillars of modern physics are fundamentally at odds with each other, and a complete theory of quantum gravity remains elusive. However, the extreme conditions around black holes, particularly near the photon sphere, offer a unique environment where both quantum and relativistic effects can be studied simultaneously. The photon sphere, as an area where photons interact with strong gravitational fields, may offer important clues about how gravity works on the smallest scales. This research could potentially lead to breakthroughs in our understanding of quantum black holes, wormholes, and other exotic phenomena. In this sense, the photon sphere acts as a bridge between two of the most important, yet incompatible, theories in physics. Moreover, studying the photon sphere can help clarify the concept of spacetime itself. General relativity tells us that massive objects warp the fabric of spacetime, but the true nature of this curvature remains poorly understood, particularly in extreme environments like those near black holes. As light follows the curve of spacetime around a black hole, we gain insight into the geometry of the universe at its most extreme. This can inform future studies of how spacetime behaves under extreme conditions, shedding light on the deeper structure of the cosmos. While the photon sphere remains an area of active research, it has already begun to provide us with answers to some fundamental questions. For instance, by studying the light emitted near black holes, we can infer the properties of the objects themselves, such as their mass, spin, and charge. These measurements have already helped us confirm the existence of supermassive black holes at the centers of many galaxies. In addition, researchers are now exploring how the photon sphere might help explain the formation and behavior of certain exotic objects, such as gravitationally bound photon rings. Another intriguing possibility is that the photon sphere may help us better understand the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB is the oldest light in the universe, dating back to when the universe was only a few 100,000 years old. It has been used to study the origins of the universe, but scientists are still unraveling its mysteries. The photon sphere's role in bending and distorting light could provide new insights into the propagation of the CMB, especially as it interacts with black holes and other massive objects. The gravitational effects of black holes could alter the CMB in subtle ways, and studying these effects could help refine our models of the early universe. Furthermore, the photon sphere serves as an example of the interconnectedness of the universe. As photons orbit the black hole, they trace the contours of spacetime, illustrating how all of the fundamental forces, gravity, electromagnetism, and even quantum mechanics, interact in complex ways. The behavior of light near the photon sphere is not just a cosmic curiosity. It is a reflection of the underlying unity of the universe, a reminder that everything is interconnected in ways that we are only beginning to comprehend. In the coming years, we will likely see significant advancements in our ability to observe and study black holes and their photon spheres. As new technologies and theories emerge, our understanding of these phenomena will deepen, providing even more profound insights into the nature of light, gravity, and the cosmos itself. The photon sphere represents an exciting frontier in science, one that will continue to challenge our understanding of the universe for many years to come. As we continue to explore the mysteries of the photon sphere, it becomes clear that it is more than just a place where light gets trapped. It symbolizes the threshold where our understanding of the universe is stretched to its limits. This region, where photons are caught in the powerful gravitational influence of a black hole, holds the key to understanding some of the most profound questions in physics. One of the key aspects of the photon sphere that we haven't touched on yet is its connection to the study of gravitational waves. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. These waves travel at the speed of light, carrying with them information about the objects that created them. The photon sphere, as a critical area around black holes, plays a significant role in shaping the gravitational waves we detect here on Earth. When black holes interact with their surroundings, whether through the accretion of matter or the merging of two black holes, the intense gravitational forces involved can produce gravitational waves that reverberate across the cosmos. As these waves travel through space, they distort the photon sphere's light, adding a unique signature to the pattern of gravitational waves detected by observatories like LIGO and Virgo. By studying how the photon sphere reacts to these waves, scientists can refine their understanding of both gravitational waves and the dynamics of black holes. Furthermore, the photon sphere has been proposed as a possible source of high-energy radiation, including gamma rays and X-rays. When matter is caught in the gravitational grip of a black hole, it accelerates to incredibly high speeds, producing immense amounts of energy. This energy can be released in the form of radiation, which may be emitted from the photon sphere itself. The interaction of light with the black hole's gravity can lead to the emission of extremely high-energy photons that can be detected by space-based telescopes like the Hubble Space Telescope or the Chandra X-ray Observatory. The study of this radiation offers more than just a glimpse into the physical processes surrounding black holes. It provides scientists with the opportunity to investigate the behavior of light in extreme environments, testing the limits of our current understanding of physics. In particular, it could help us better understand the relationship between matter, energy, and the curvature of spacetime. The potential for new discoveries does not stop there. As technology continues to advance, scientists are developing new methods for studying black holes and the photon sphere in greater detail. One such method is the use of extremely high-resolution imaging techniques, such as the Event Horizon Telescope, EHT, which was responsible for capturing the first-ever image of a black hole's event horizon in 2019. The EHT uses a network of radio telescopes around the world to observe the very heart of black holes, and future upgrades to this network may allow us to study the photon sphere with unprecedented precision. One of the most exciting aspects of these observations is the possibility of capturing images of the photon sphere itself. As light gets caught in orbit around the black hole, it forms a luminous ring, the photon ring, that encircles the black hole's event horizon. This ring represents the photon sphere's most visible manifestation and provides us with a direct visual clue as to the behavior of light in the extreme gravitational environment near a black hole. With improved imaging techniques, scientists may soon be able to capture clearer, more detailed images of these photon rings, which would offer new insights into the structure and dynamics of black holes. The study of the photon sphere also has significant implications for our understanding of the nature of black holes. One of the most intriguing questions in modern physics is the ultimate fate of matter and energy that falls into a black hole. As we've discussed, the photon sphere is the point at which photons can get trapped in orbit, but what happens to objects that cross this threshold and continue on toward the event horizon? The nature of the event horizon remains one of the most baffling mysteries in physics. Is it a boundary beyond which nothing can escape? Or is it a more subtle region that allows information to escape in some way, possibly in the form of Hawking radiation? While we don't yet have answers to these questions, the photon sphere serves as a crucial piece of the puzzle. By studying the light that orbits around the black hole, scientists can infer the conditions near the event horizon and gain new insights into the black hole's structure. This research may one day lead to a deeper understanding of what happens inside a black hole and whether information can truly be lost, as some theories suggest, or if there are ways for information to escape from the singularity. The photon sphere also holds potential for testing alternative theories of gravity. While general relativity has been incredibly successful in describing the behavior of gravity in most situations, there are still unresolved questions, especially when it comes to the behavior of gravity in extreme environments like those near black holes. The photon sphere offers a natural laboratory for testing alternative theories, such as those involving quantum gravity or modifications to general relativity, by observing how light behaves in its strong gravitational field. Additionally, the photon sphere plays a significant role in the ongoing search for new physics. As we've mentioned, studying the effects of light in this region could provide valuable insights into the nature of dark matter, dark energy, and other exotic phenomena that remain largely mysterious. By observing how light interacts with the photon sphere, we may be able to detect signatures of these elusive forces, which could lead to major breakthroughs in our understanding of the universe. The potential implications of the photon sphere extend far beyond the study of black holes. As we continue to observe and analyze these cosmic phenomena, we are not only learning more about the extreme environments that exist in the universe but also gaining deeper insights into the fundamental laws of physics. The photon sphere represents a unique laboratory in which the forces of gravity, light, and spacetime all interact in intricate ways, offering us a glimpse into the heart of some of the most perplexing mysteries of the cosmos. The photon sphere is not just a region around a black hole where photons are trapped in orbit. It is a place of extreme gravitational forces, time dilation, and light distortion, offering scientists a valuable tool for exploring the nature of light, gravity, and the very fabric of spacetime. Through the study of this fascinating phenomenon, we can continue to probe the depths of black holes, testing the limits of our understanding of the universe and pushing the boundaries of physics. As we look to the future, it is clear that the photon sphere will continue to play a central role in our exploration of space. Whether through the study of gravitational waves, the detection of high-energy radiation, or the development of new imaging techniques, this enigmatic region holds the potential to unlock some of the most profound mysteries of the cosmos. And as we continue to unravel the secrets of black holes and the photon sphere, we will gain a deeper understanding of the universe and our place within it, one that is sure to inspire awe and wonder for generations to come. The photon sphere is a truly fascinating aspect of black hole physics, one that continues to captivate researchers and enthusiasts alike. What makes it especially intriguing is that it challenges our understanding of the basic nature of light, gravity, and the fabric of space and time. This unique area around the black hole, where light can be caught in orbit, invites questions that are fundamental to our understanding of the universe. For example, how does the curvature of spacetime affect the behavior of light? And what happens to the structure of spacetime in extreme environments? When we observe the photon sphere in theoretical models, it serves as a stark reminder of how dramatically gravitational forces change the flow of light. Light, the fastest thing in the universe, becomes trapped. The idea that even light, which travels at the speed of 300,000 kilometers per second, can fall victim to the immense gravitational pull of a black hole underscores just how extreme these objects are. No longer a mere concept of distant celestial bodies, black holes have transformed from a theoretical idea to a focus of intense study due to advancements in technology, allowing us to probe their surrounding environments in unprecedented detail. As we venture deeper into the realm of black holes, we come to realize that the photon sphere plays an important role in understanding the larger cosmic phenomena at work. The fact that photons are not just emitted and absorbed but can exist in a state of perpetual orbit represents one of the most extreme behaviors of light in our universe. But as you dive into the details, you find that these concepts aren't as straightforward as they seem. It's as though the universe itself is saying, "There's more to discover." The environment surrounding black holes is so extreme that it warps our standard understanding of physics. The theory of relativity, especially in its general form, tells us that mass warps spacetime, creating the gravitational well that makes the photon sphere possible. But what happens in such a warped region? How does spacetime behave under such conditions? And how do we translate these effects into observable phenomena? These questions don't have simple answers. For example, one curious phenomenon that arises in the photon sphere is the idea of gravitational lensing. Gravitational lensing occurs when light from a distant star or galaxy passes near a massive object like a black hole, bending due to the curvature of spacetime. This bending of light can create multiple images of the same object, or even magnify the light from faraway objects, allowing us to observe phenomena that would otherwise be hidden. Gravitational lensing near the photon sphere is particularly strong, offering a unique opportunity for astronomers to study the effects of black holes on light itself. Another intriguing aspect of the photon sphere is its relationship with the event horizon. The event horizon is often referred to as the point of no return. Once an object crosses this boundary, it is impossible for anything, even light, to escape. In contrast, the photon sphere exists just outside this region, where photons can orbit but aren't necessarily doomed to fall into the black hole. The space between the photon sphere and the event horizon, known as the innermost stable orbit, is a crucial zone for understanding how matter behaves near a black hole. It's a delicate balance, too close to the event horizon, and everything is swallowed up by the black hole's immense gravity, just far enough away, and objects can be trapped in an orbit that may last indefinitely. This raises the question, can we ever hope to directly observe the photon sphere in action? While we've already made incredible progress in observing black holes, such as the Event Horizon Telescope capturing the first image of a black hole's shadow, the photon sphere remains a particularly challenging object to study. The closest we may come to observing it is through the effects it has on light, matter, and gravitational waves. Yet, by studying the interactions between light and gravity near a black hole, we can learn more about how these mysterious objects affect the structure of spacetime itself. As we delve deeper into these complex ideas, it becomes clear that the photon sphere is more than just a theoretical curiosity. It offers a glimpse into some of the most extreme conditions in the universe, conditions where our current understanding of physics, both classical and quantum, begins to break down. This is where science and imagination intersect, where the most intriguing and perplexing questions await answers. The photon sphere also pushes the boundaries of our technological capabilities. As we develop more advanced instruments to study black holes, we continue to refine our models of how light behaves in the presence of such immense gravitational forces. For example, telescopes that operate in different parts of the electromagnetic spectrum, such as radio, infrared, and X-ray observatories, give us different insights into the behavior of photons near black holes. These observations allow us to piece together the puzzle of the photon sphere from multiple perspectives, each revealing new details about the forces at play in these enigmatic regions. One particularly exciting development in black hole research is the ongoing efforts to understand the connection between black holes and quantum mechanics. At the photon sphere, where light behaves in unexpected ways, we find ourselves at the intersection of general relativity, which describes the behavior of large-scale objects, and quantum mechanics, which governs the behavior of particles at the smallest scales. The photon sphere presents an opportunity to explore the tension between these two theories, and it may be in this strange and extreme environment that we find the key to unlocking the true nature of reality. Consider the idea of Hawking radiation, which suggests that black holes may not be entirely black. Instead, they could emit radiation as a result of quantum processes near the event horizon. If photons near the photon sphere are influenced by such processes, they may carry information about the quantum nature of black holes. This opens up fascinating possibilities for future research, as scientists work to understand how quantum effects might manifest in black holes, and how they could impact the properties of the photon sphere itself. Furthermore, the study of the photon sphere could help us answer fundamental questions about the nature of gravity. While general relativity provides a powerful framework for understanding gravity, it does not account for the full range of quantum effects that occur in extreme environments. The photon sphere, as a region where light and gravity interact in highly unusual ways, provides a natural laboratory for testing the limits of our understanding of gravity. By studying how light behaves in the photon sphere, scientists can probe the nature of gravitational forces and search for new insights into the fundamental workings of the universe. As we continue to explore the photon sphere, we are not only studying the behavior of light near black holes but also investigating the most fundamental aspects of the universe itself. The interplay between light, gravity, and spacetime offers a window into the heart of one of the most profound mysteries of the cosmos. And as our understanding of this enigmatic region deepens, we may uncover answers to some of the most profound questions in physics, shedding new light on the nature of the universe and our place within it. The exploration of the photon sphere continues to offer new avenues for scientific discovery. As we dive deeper into understanding its complexities, we encounter a fascinating interplay of theoretical physics, observational astronomy, and cutting-edge technology. The potential implications of understanding the photon sphere are vast, and they promise to reshape our understanding of black holes, gravity, light, and even the fundamental laws of nature. One of the most exciting aspects of studying the photon sphere is the ability to test the very limits of our current theories. The photon sphere sits at the crossroads of general relativity, which governs large-scale gravitational forces, and quantum mechanics, which explains the behavior of particles at the smallest scales. This is a region where the two theories collide, and where we might finally get clues to one of the most elusive goals in physics: the unification of general relativity and quantum mechanics. The photon sphere is also a reminder of the true enormity of black holes and their gravitational influence. Black holes are often portrayed as cosmic vacuum cleaners, pulling in everything around them, but the photon sphere adds a layer of complexity to this image. Light, the fastest thing in the universe, cannot escape the black hole's gravity once it enters the event horizon. However, just outside of this boundary, within the photon sphere, light can exist in a precarious orbit. This strange phenomenon challenges our intuition and shows how extreme black holes are in their influence over spacetime. Astronomers are using every tool at their disposal to study these extreme environments. With the advancement of gravitational wave detectors, such as LIGO and Virgo, and the Event Horizon Telescope, which captured the first ever image of a black hole, scientists are beginning to piece together more detailed and accurate pictures of the regions surrounding black holes, including the photon sphere. These tools are providing unprecedented insights into the behavior of light and matter near black holes, allowing scientists to test the predictions of general relativity and probe the mysteries of the photon sphere. For example, in 2019, the Event Horizon Telescope collaboration released the first image of a black hole in the galaxy M87. This was a monumental achievement, as it provided the first direct visual evidence of the shadow of a black hole, which is formed by the photon sphere and the event horizon. While the image itself did not directly capture the photon sphere, it was a breakthrough that confirmed many theoretical predictions about black holes, including the fact that the region surrounding the event horizon is warped and curved, with light being bent in unusual ways. The study of the photon sphere also opens up exciting possibilities for observing the effects of black holes on their surroundings. As photons are caught in orbit around the photon sphere, they interact with the intense radiation and magnetic fields present near black holes. These interactions can lead to the formation of powerful jets of energy that shoot out from the black hole's poles. These jets are among the most energetic phenomena in the universe, and they offer a glimpse into the extreme conditions near black holes. Through the study of the photon sphere, scientists can also learn more about the fate of matter that falls toward a black hole. Matter that enters the photon sphere may be trapped in orbit for a time, but eventually, it will either be flung out into space or drawn into the event horizon. This process, known as accretion, is one of the key ways in which black holes grow and evolve. By observing how light and matter behave near the photon sphere, astronomers can gain insights into the complex dynamics of accretion disks, the structures that form around black holes as matter spirals inward. The photon sphere also offers new possibilities for exploring the fundamental nature of light itself. Light in the photon sphere is subject to the intense gravitational forces of the black hole, and its behavior can be drastically altered. For example, photons in the photon sphere can experience gravitational redshift, a phenomenon in which the wavelength of light is stretched due to the influence of gravity. This stretching can cause light to lose energy and shift toward the red end of the spectrum. By studying gravitational redshift in the photon sphere, scientists can learn more about the curvature of spacetime and the effects of gravity on light. Furthermore, the photon sphere provides a unique opportunity to study the fundamental nature of spacetime itself. In the vicinity of black holes, spacetime is stretched and warped in extreme ways. The curvature of spacetime near the photon sphere is so intense that light can be bent in tight orbits. This warping of spacetime can also affect the path of other objects, such as spacecraft or even stars. By studying the behavior of light and matter in the photon sphere, scientists can test the predictions of general relativity and probe the very structure of spacetime in one of its most extreme forms. The implications of studying the photon sphere extend beyond the realm of black hole research. Understanding the behavior of light in such extreme conditions could have profound implications for our broader understanding of the universe. For example, it may shed light on the nature of dark matter and dark energy, the mysterious substances that make up the majority of the universe's mass and energy but remain largely undetectable. The interactions between light and gravity in the photon sphere could reveal new insights into the properties of dark matter and how it affects the universe on the largest scales. Additionally, the study of the photon sphere could help us unlock the secrets of the early universe. The conditions near a black hole are reminiscent of the conditions in the very early universe, when spacetime was hot and dense. By studying the photon sphere, we may gain insights into the behavior of light and matter under these extreme conditions, which could help us understand the origins of the universe itself. This connection between black holes and the early universe underscores the importance of studying these enigmatic objects in order to gain a deeper understanding of the fundamental processes that shape the cosmos. As our observational technology continues to improve, we are likely to uncover even more mysteries about the photon sphere and the behavior of light near black holes. Future space missions, such as the James Webb Space Telescope and the proposed LISA Gravitational Wave Observatory, promise to provide even more detailed observations of black holes and their surrounding environments. With these new tools, scientists will be able to push the boundaries of our knowledge and answer some of the most profound questions in physics. The photon sphere, with its strange properties and its connection to the most extreme phenomena in the universe, represents one of the most exciting frontiers in modern astrophysics. Its study offers the potential to unlock new insights into the nature of gravity, light, and the fundamental forces of the universe. As we continue to probe the depths of space and explore the mysteries of black holes, we are bound to discover even more about this enigmatic region, and with it, our understanding of the cosmos will grow ever deeper. As we continue to explore the fascinating world of the photon sphere, it's important to acknowledge how these discoveries might alter the future of our understanding of space itself. The study of black holes and the photon sphere intersects with some of the most profound questions in science. Questions about the nature of space, time, and the very fabric of reality. The photon sphere, due to its bizarre properties, challenges our conventional ideas about how light and gravity interact. Since light is typically thought of as the fastest thing in the universe, it seems strange to consider the possibility that it could be trapped in orbit around a black hole. The photon sphere presents us with the unusual idea that light, despite its incredible speed, is not always able to escape the pull of a black hole's gravity. And this, in turn, forces us to reconsider our understanding of spacetime itself. One of the more intriguing aspects of the photon sphere is the notion that light can be trapped in multiple orbits around a black hole. These orbits, however, are not stable like the orbits of planets around a star. Light within the photon sphere can be diverted from its circular path by even the slightest disturbance, such as the gravitational influence of nearby objects, or even the emission of energy from the black hole itself. This makes the photon sphere a delicate balance, where tiny fluctuations can cause photons to either spiral inward toward the event horizon or be ejected into space. This phenomenon highlights just how intense the forces near a black hole truly are. The photon sphere is one of the few places in the universe where gravity is so strong that it can alter the very path of light. This challenges our understanding of what light can and cannot do and opens up new possibilities for studying the interaction between gravity and electromagnetic radiation. One of the areas of scientific investigation that could benefit immensely from studying the photon sphere is the behavior of accretion disks, the swirling disks of gas, dust, and other matter that form around black holes. These disks are heated to extremely high temperatures as the material spirals inward, and they often emit enormous amounts of radiation in the process. The photons that make up this radiation can interact with the photon sphere, which could provide new insights into the dynamics of the accretion process. Moreover, the behavior of the photon sphere could offer valuable information about the properties of the black hole itself. Since the photon sphere exists just outside the event horizon, it's the closest region we can observe before crossing into the realm where light can no longer escape. By carefully analyzing the light and other radiation emitted from the vicinity of the photon sphere, scientists can infer key properties of the black hole, such as its mass, spin, and charge. This is important because it provides us with a way to indirectly study black holes without needing to directly observe the event horizon, an impossibility given that nothing, not even light, can escape from it. In fact, one of the most profound implications of studying the photon sphere is that it offers a method for testing Einstein's theory of general relativity in one of the most extreme environments possible. General relativity, which describes how gravity operates on large scales, has been extensively tested in many situations, but studying the photon sphere allows scientists to probe its predictions in ways that were previously impossible. The extreme conditions near black holes push general relativity to its limits, and understanding how light behaves in these conditions can help us to understand whether the theory remains accurate, or if there are deviations that could point toward new physics. One of the most exciting aspects of the photon sphere is its potential as a tool for studying the structure of spacetime itself. We know that spacetime is not a static backdrop. It is a dynamic entity that can be warped and distorted by mass and energy. The photon sphere, with its highly curved spacetime and strange gravitational effects, offers a glimpse into the very nature of spacetime at its most extreme. By studying how light behaves in this region, scientists may be able to unlock new insights into the underlying fabric of the universe, perhaps even offering clues about the quantum nature of gravity, a theory that has eluded physicists for decades. The future of studying the photon sphere is also tied to technological advancements. As our instruments and observational capabilities improve, we will be able to gather even more detailed data about black holes and their environments. For instance, gravitational wave observatories like LIGO and Virgo are already providing us with valuable information about black hole mergers and the ripples in spacetime that they produce. These detectors are likely to become even more sensitive in the coming years, allowing us to study the effects of the photon sphere in greater detail. Similarly, the upcoming launch of the James Webb Space Telescope, JWST, promises to provide astronomers with the ability to observe black holes and their environments in unprecedented detail. With its advanced infrared capabilities, JWST could potentially capture the radiation emitted from near the photon sphere, giving us a clearer picture of this enigmatic region. Additionally, the proposed LISA, Laser Interferometer Space Antenna, mission, which will focus on detecting gravitational waves, could also help in understanding the dynamics around black holes and the photon sphere. Another emerging area of research is the development of new computational models and simulations that can help scientists simulate the behavior of light and matter near black holes. These simulations are becoming increasingly sophisticated, allowing scientists to model the effects of the photon sphere in more accurate and detailed ways. As the computational power of supercomputers increases, these simulations will continue to improve, providing more precise predictions and helping to validate the theoretical predictions of general relativity. In addition to advancing our understanding of black holes, the study of the photon sphere has broader implications for our understanding of the universe as a whole. The photon sphere, with its extreme conditions and its role in the behavior of light and matter, offers a window into some of the most fundamental questions in physics. It challenges our understanding of how gravity works, how light behaves, and how the universe itself operates on the most fundamental levels. One of the most exciting possibilities is that the study of the photon sphere may eventually lead to breakthroughs in other areas of physics. For example, the behavior of light in extreme gravitational fields could shed light on the nature of dark matter and dark energy. These mysterious substances, which make up the majority of the universe's mass and energy, have thus far eluded direct detection. However, by studying the effects of gravity and light near black holes, we may be able to gain new insights into these invisible components of the universe. Moreover, the photon sphere provides an opportunity to test the boundaries of our understanding of quantum mechanics. In the extreme conditions near a black hole, where both gravity and quantum effects are significant, we may uncover clues about how these two seemingly incompatible theories, general relativity and quantum mechanics, can be reconciled. This could be the key to unlocking a theory of quantum gravity, one of the most sought-after goals in modern physics. As our knowledge of black holes and the photon sphere continues to grow, we are bound to uncover more mysteries and challenges. Every new discovery in this area adds another layer of complexity to our understanding of the cosmos, and each breakthrough brings us one step closer to answering some of the most profound questions in science. The photon sphere remains one of the most captivating phenomena in the universe. It serves as a reminder of just how strange and mysterious the universe can be, and it invites us to challenge our assumptions about the nature of reality. As we continue to explore this enigmatic region and study its effects, we are bound to unlock even more secrets about the nature of light, gravity, and the very structure of spacetime. The photon sphere is not just a theoretical construct, but a physical reality that lies at the heart of black hole physics. The closer we get to the event horizon, the more extreme the conditions become. Understanding the photon sphere is vital, not only for studying black holes but also for developing a deeper understanding of how the laws of physics operate under extreme conditions. One of the most crucial aspects of this region is how it defies our everyday expectations of how light behaves, and by exploring this further, we may be able to answer some of the most fundamental questions in physics. When we observe light near a black hole, it's not like observing light around more familiar objects like stars or planets. Instead, the immense gravitational field of the black hole warps spacetime, bending the path of light in such a way that photons are caught in a loop. This phenomenon challenges the classical view of light as something that always travels in straight lines. Instead, light near a black hole is forced to follow the curvature of spacetime, effectively creating paths that lead photons into orbit. But this doesn't mean that light is forever trapped at the photon sphere. The photon sphere is not a stable orbit. Instead, it represents a precarious balance where photons can either be sent spiraling inward toward the black hole or ejected outward into space. These unstable orbits occur at a critical point between being bound to the black hole and escaping its pull entirely. Understanding why the photon sphere is unstable is key to understanding the nature of black holes and their effect on the surrounding space. For any photon at this critical distance, the slightest disturbance, whether it's from another particle, gravitational wave, or even the slightest change in the black hole's spin, can alter the photon's path and force it into a new trajectory. This makes the photon sphere an unpredictable and chaotic region, where the laws of physics are pushed to their limits. The light that we observe coming from the photon sphere could therefore hold untold secrets, but it's far from simple to interpret. Studying this light requires advanced techniques that combine both observational data and theoretical models, pushing our understanding of the universe further. Interestingly, the instability of the photon sphere doesn't mean that light within it is useless to scientists. In fact, it provides us with one of the clearest windows into the behavior of black holes. Even though the light emitted near the photon sphere is subject to extreme forces, it can still be observed, albeit with great difficulty. In particular, the light that escapes from just outside the photon sphere can give us critical insights into the structure of the black hole itself. By studying the spectral signatures of this light, scientists can infer details about the black hole's mass, spin, and even its charge. There are many challenges to observing light from the photon sphere directly, and one of the main reasons for this is that the photon sphere lies so close to the event horizon. The event horizon is the boundary beyond which nothing can escape, not even light. As a result, the light that escapes from the photon sphere has to be incredibly powerful to overcome the gravitational pull of the black hole and reach observers. But even so, the light that does manage to escape provides an invaluable probe of the black hole's properties. Recent advancements in observational technology have made it possible to study the regions near black holes in greater detail than ever before. The Event Horizon Telescope, EHT, for example, made history in 2019 by capturing the first ever image of a black hole's event horizon. This breakthrough was a monumental achievement in black hole research and opened the door to new ways of studying the photon sphere. While the image captured by the EHT was not taken at the photon sphere itself, it provided the first clear image of the region surrounding a black hole, bringing us one step closer to understanding the complex dynamics at play. The potential for studying black holes in this way is immense. As technology continues to improve, we are likely to see more detailed observations of the region near the photon sphere. Future space-based telescopes, such as the James Webb Space Telescope, could provide additional insights into the dynamics of the photon sphere, allowing us to observe how light behaves as it interacts with the black hole's gravitational forces. This could help refine our models of black holes, providing clearer images and more accurate measurements of their properties. The photon sphere also plays a significant role in one of the most puzzling phenomena in modern astronomy: gravitational lensing. Gravitational lensing occurs when the light from distant objects is bent by the gravitational influence of a massive object, like a black hole. The photon sphere is one of the key regions where gravitational lensing takes place, as the light passing through this region is bent and distorted by the black hole's immense gravitational field. The result is a phenomenon known as the Einstein ring, where the light from a distant object is bent into a circular shape, creating a distorted image of the original source. Gravitational lensing is not just a curious effect, it has real applications for astronomers. By studying the distortions caused by gravitational lensing, scientists can learn more about the mass distribution of objects like black holes and galaxies. In the case of black holes, gravitational lensing can help us determine their mass, spin, and even the nature of their event horizon. This makes the photon sphere an essential region for observing the effects of gravitational lensing and gaining a deeper understanding of the properties of black holes. In addition to gravitational lensing, the photon sphere is also related to another fascinating phenomenon known as photon ring emission. The photon ring is a signature produced by light that has been trapped in unstable orbits around the black hole. This ring-like structure is a direct result of the extreme gravitational forces near the photon sphere, and it provides another way to study the region around black holes. These photon rings are incredibly difficult to detect, as they are often faint and easily drowned out by the intense radiation from the black hole's accretion disk. However, with the right tools, scientists can potentially detect these elusive photon rings and use them to learn more about the behavior of light near black holes. The study of the photon sphere also has profound implications for our understanding of the ultimate fate of light and information in the universe. At the heart of many theories about the nature of black holes is the idea of the information paradox. This paradox arises from the question of what happens to the information that falls into a black hole. According to general relativity, information should be lost forever once it crosses the event horizon. However, quantum mechanics suggests that information cannot be destroyed, leading to a fundamental conflict between these two theories. The photon sphere plays a crucial role in this debate. Since light within the photon sphere can sometimes escape the black hole's gravitational pull, it raises the possibility that information could be preserved in some form. The study of how light behaves near the photon sphere, and whether it can carry information out of the black hole, could provide new insights into the resolution of the information paradox. If we can understand how light interacts with the black hole's gravitational field, we might be able to uncover new ways to reconcile general relativity with quantum mechanics, shedding light on one of the deepest mysteries in modern physics. As our understanding of the photon sphere deepens, we are also likely to discover even more about the strange and mysterious behavior of black holes. These cosmic monsters continue to surprise us with their complexity, and as we refine our observational techniques and theoretical models, we will undoubtedly uncover new and fascinating aspects of the universe's most enigmatic objects. In the coming decades, we are likely to witness major advancements in our understanding of the photon sphere. As we continue to study black holes with increasingly sophisticated tools, we will unlock new secrets about the nature of spacetime, gravity, and light. The photon sphere, with its bizarre and counterintuitive properties, will continue to challenge our understanding of the universe and keep us pushing the boundaries of science. The photon sphere represents one of the most extraordinary phenomena in the cosmos. Located just outside the event horizon of a black hole, it serves as a region where light is trapped in orbits due to the extreme gravitational forces at play. Studying this strange and elusive region is essential for advancing our understanding of black holes and the very fabric of spacetime. As our observational technology improves, we will continue to explore the mysteries of the photon sphere, opening up new avenues for scientific discovery and potentially resolving some of the most fundamental questions in physics. As we move forward in our understanding of the photon sphere, the implications of studying it extend beyond just the realm of black holes. The photon sphere is deeply connected to some of the most fundamental aspects of physics, such as general relativity, quantum mechanics, and the nature of light itself. As researchers continue to explore this mysterious region, we can expect new breakthroughs that may reshape our understanding of the universe. One of the most intriguing aspects of the photon sphere is its connection to the concept of gravitational time dilation. This phenomenon, predicted by Einstein's theory of general relativity, suggests that time passes more slowly in stronger gravitational fields. As we approach a black hole, the gravitational pull becomes so intense that time itself seems to stretch out. Near the photon sphere, this effect becomes particularly pronounced. If we were somehow able to observe the photon sphere from a safe distance, we would see that photons near the photon sphere are caught in a slow dance, their paths distorted by the immense gravitational pull of the black hole. This effect is a direct consequence of time dilation, and it illustrates the profound impact that black holes have on the fabric of spacetime. The concept of time dilation around black holes is not just theoretical, it has been observed in other contexts as well. For example, the effects of time dilation have been measured in satellites orbiting the Earth, where time passes slightly more slowly for astronauts than it does for people on the ground. In the case of black holes, however, the effect is magnified to an extraordinary degree. The closer we get to the photon sphere, the more pronounced the time dilation becomes. In theory, at the photon sphere itself, time would appear to come to a complete stop for an outside observer. This means that photons caught in this region would seem to be frozen in time, trapped in their orbits for eternity. However, the phenomenon of time dilation raises a fascinating question: what would it be like for an object or observer that is actually inside the photon sphere? From the perspective of an observer falling toward the black hole, time would appear to proceed as normal. The experience of time would feel no different, but from the perspective of an outside observer, the passage of time would be dramatically altered. As the observer approaches the photon sphere, they would appear to slow down, and once they cross into this region, they would seem to freeze in time entirely. This creates a kind of paradox, where time behaves in fundamentally different ways depending on one's point of view. The study of time dilation and the photon sphere also leads us to a deeper understanding of the nature of light. Photons, the particles that make up light, are massless. In the presence of intense gravitational fields, like those near a black hole, photons still follow the curvature of spacetime, as if they were influenced by mass. This behavior challenges our classical understanding of light and demonstrates the interconnectedness of space, time, and gravity. The fact that photons can be trapped in orbits around a black hole suggests that the very fabric of spacetime is more dynamic and complex than we ever imagined. Beyond the mathematical and theoretical implications, the photon sphere holds tremendous potential for practical applications as well. By observing how light behaves near a black hole, we can learn more about the fundamental properties of the universe. For example, by studying the spectral signatures of light emitted from the photon sphere, we can gather valuable information about the black hole's mass, spin, and even its electric charge. These measurements could provide insights into the processes occurring in the region surrounding the black hole, such as the accretion of matter and the formation of relativistic jets. In fact, the study of the photon sphere could lead to groundbreaking discoveries about the nature of the event horizon. The event horizon, the boundary beyond which nothing can escape a black hole, is one of the most mysterious aspects of black hole physics. Understanding how light behaves near the photon sphere can help us better understand the properties of the event horizon itself. For example, it may help us determine whether information can escape a black hole in any form, which could have profound implications for the resolution of the information paradox. This paradox, which arises from the conflict between general relativity and quantum mechanics, remains one of the most pressing unresolved questions in theoretical physics. The photon sphere, with its complex interactions between light and gravity, may hold the key to unlocking this mystery. Furthermore, the study of black holes and the photon sphere also has profound implications for our understanding of the universe's larger structure. Black holes are not isolated objects. They are part of a larger cosmic web of matter and energy. Their gravitational influence extends far beyond their immediate surroundings, and by studying the light that escapes from near the photon sphere, we can learn more about the distribution of mass and energy in the universe. This could help us better understand the formation and evolution of galaxies, as well as the role that black holes play in shaping the cosmos. The photon sphere also plays a crucial role in the study of gravitational waves. Gravitational waves, ripples in spacetime caused by the acceleration of massive objects, have become one of the most exciting areas of research in modern astrophysics. The detection of gravitational waves has opened up a new way of observing the universe, and black holes are one of the primary sources of these waves. The photon sphere, with its dynamic and unstable orbits, is a key region where gravitational waves are generated. By studying the behavior of gravitational waves near black holes, we can learn more about the underlying mechanics of the photon sphere and gain deeper insights into the nature of spacetime itself. The possibility of detecting gravitational waves from the photon sphere represents one of the most exciting frontiers in astrophysical research. With the development of more advanced detectors, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, scientists are now able to observe the faint ripples in spacetime produced by the collision and merger of black holes. These events produce massive amounts of energy, and the gravitational waves they generate can carry information about the properties of the black holes involved, including their masses, spins, and the dynamics of the photon sphere. The detection of such waves could provide us with an unprecedented opportunity to probe the inner workings of black holes and the nature of the photon sphere. As we continue to explore the mysteries of the photon sphere, we are likely to encounter even more paradoxes and mysteries that challenge our understanding of the universe. The photon sphere represents a region of extreme gravitational forces, where the very fabric of spacetime is stretched and warped to its limits. It is a place where light behaves in strange and unexpected ways, and where the laws of physics themselves are tested to their limits. The more we learn about this enigmatic region, the more we come to realize that black holes are not just strange cosmic objects, but windows into the most fundamental truths about the universe. The photon sphere also has important implications for our understanding of the future of the universe. As we continue to probe the deepest reaches of space, the study of black holes and the photon sphere could help us answer some of the most profound questions about the ultimate fate of the cosmos. Will the universe continue to expand forever, or will it eventually collapse in on itself, creating a big crunch? What role do black holes play in the evolution of the universe? And what will happen to the information that falls into them? These are questions that have puzzled scientists for decades, and the study of the photon sphere may provide the key to unlocking these mysteries. In the coming years, the study of the photon sphere and black holes will continue to evolve. With advancements in observational technology and theoretical models, we are likely to uncover new insights into the nature of these enigmatic cosmic objects. As we push the boundaries of our knowledge, we may discover new phenomena that challenge our understanding of the universe and force us to rethink the very laws of physics. The photon sphere, with its strange and unpredictable behavior, is just one example of the many mysteries that lie waiting for us in the depths of space. The photon sphere is more than just a theoretical concept. It is a key to understanding the universe itself. By studying the behavior of light and gravity near black holes, we can uncover some of the most fundamental secrets of the cosmos. Whether through the observation of gravitational waves, the detection of photon rings, or the study of time dilation, the photon sphere offers us a unique and fascinating glimpse into the workings of the universe at its most extreme. The study of the photon sphere is intricately tied to some of the most profound and puzzling concepts in modern physics, not only enhancing our understanding of black holes but also opening the door to new realms of astrophysics and cosmology. As we continue to probe deeper into the heart of black holes, the photon sphere presents a fascinating avenue of exploration, challenging both our theoretical models and our technological capabilities. One of the most significant questions in black hole physics is how we can observe and study the photon sphere directly. After all, the very nature of black holes means that we cannot simply observe them in the traditional sense. The event horizon, the point beyond which nothing can escape, including light, renders direct observation near the black hole impossible. However, advances in observational technology are slowly bridging the gap between theory and reality. Instruments like the Event Horizon Telescope, EHT, which famously captured the first-ever image of a black hole's event horizon, are now capable of looking at the regions surrounding black holes in unprecedented detail. The Event Horizon Telescope, in particular, has been instrumental in bringing us closer to understanding the photon sphere. While the telescope's primary goal was to capture the shadow of a black hole, the data collected allows scientists to study the behavior of light and radiation in the intense gravitational fields around black holes. This means that while we cannot directly observe the photon sphere itself, we can gather indirect evidence of its existence by analyzing the light that is bent, distorted, and even captured by the black hole's gravitational influence. The EHT's work has already provided us with a glimpse into how light behaves in such extreme environments, providing clues about the photon sphere's role in shaping the light we see around black holes. The photons that are caught in the photon sphere travel in paths that are highly curved, influenced by the immense gravity of the black hole. This means that their trajectories can be altered and deflected in unexpected ways, giving rise to optical phenomena like gravitational lensing. Gravitational lensing occurs when light from distant stars or other objects passes near a black hole and is bent by its gravity. This bending causes the light to follow a curved path, creating multiple images or even making objects appear where they would otherwise be invisible. In some cases, the photon sphere itself can act as a sort of natural lens, amplifying or distorting the light from behind the black hole. Through this phenomenon, scientists are able to map out the region surrounding black holes and gather important information about their structure. For example, by observing the distortions in the light caused by gravitational lensing, astronomers can infer the mass and spin of a black hole. This is crucial for understanding the properties of the photon sphere and how it interacts with light. Additionally, gravitational lensing has the potential to provide insights into the geometry of spacetime itself. The bending of light reveals how the fabric of space is warped by the black hole's gravity, offering a direct window into the nature of spacetime near a singularity. However, as intriguing as gravitational lensing and indirect observations may be, they are only part of the story. The photon sphere is a region of immense gravitational forces, and understanding its full implications requires us to go beyond simply observing the effects of these forces. In recent years, researchers have begun to explore the possibility of directly detecting the signals emitted from the photon sphere itself, especially in the form of high-energy radiation such as X-rays and gamma rays. These high-energy emissions could provide critical insights into the conditions near the photon sphere, revealing the behavior of particles and fields in this extreme environment. The possibility of directly detecting emissions from the photon sphere also opens up new avenues for understanding the interaction between black holes and their surrounding environments. Black holes are often surrounded by accretion disks, which are made up of hot, ionized gas that spirals inward toward the event horizon. The photon sphere lies just above the event horizon, and the material in the accretion disk is subject to the same gravitational forces that influence light. As particles in the disk move closer to the black hole, they are accelerated to incredibly high velocities, and this intense energy can produce radiation. Some of this radiation could originate from or pass through the photon sphere, offering clues about the dynamics of the material in the disk and the structure of the black hole itself. This interaction between the photon sphere and the accretion disk is one of the many areas of black hole research that is still in its infancy. Scientists are only beginning to explore how light and matter interact in these extreme environments. Understanding how photons are captured and redirected by the photon sphere will require a deeper understanding of the fundamental forces at play in these regions, including gravity, electromagnetism, and the behavior of matter under intense pressure and temperature. The more we learn about these interactions, the better equipped we will be to explain the complex and often paradoxical phenomena associated with black holes. In addition to its theoretical implications, the study of the photon sphere could have practical applications in fields beyond astrophysics. For instance, the principles behind gravitational lensing have already been used in astronomy to map out the distribution of dark matter in galaxies. By studying how light is bent around black holes, scientists can learn more about the unseen mass that influences the universe's structure. Similarly, the insights gained from studying the photon sphere may have applications in areas like high-energy physics, where the behavior of particles in extreme environments could help us understand fundamental questions about the nature of the universe. As we continue to probe the mysteries of black holes and the photon sphere, it is likely that new theories and models will emerge that challenge our existing understanding of physics. One of the most exciting possibilities is the notion that black holes may be connected to other dimensions or universes, a theory that has been suggested in the context of string theory and the multiverse hypothesis. If true, this would have profound implications for our understanding of reality itself, as it would suggest that the universe we observe is only one of many possible realities. The photon sphere, with its strange and unpredictable behavior, could be a key piece of the puzzle in understanding these deeper, more fundamental questions about the nature of the cosmos. In addition to these theoretical and practical implications, the photon sphere also raises profound philosophical questions. What does it mean for light to be trapped in a region where time seems to slow down or even stop? If photons can be caught in orbit around a black hole, what does that say about the nature of time, space, and causality? These are questions that philosophers and physicists alike have pondered for centuries. The discovery of the photon sphere, and our ongoing study of it, may force us to rethink our basic assumptions about the universe and the laws that govern it. As we look ahead, the photon sphere remains one of the most enigmatic and fascinating regions in the universe. Its study promises to reveal new insights into the nature of black holes, the fabric of spacetime, and the fundamental forces that govern the cosmos. With new technologies and theories on the horizon, we are likely to uncover even more profound mysteries about the photon sphere in the years to come. The quest to understand the photon sphere and its role in the cosmos is one of the great scientific challenges of our time. It is a region where light behaves in strange and unexpected ways, a place where gravity warps the very fabric of spacetime. Yet, despite its mysterious nature, the photon sphere holds the potential to unlock some of the most profound secrets of the universe. As our understanding deepens and our ability to observe these extreme environments improves, we may one day come to realize that the photon sphere is not just a peculiar feature of black holes, but a key to unlocking the ultimate truths of the cosmos. As we venture further into the study of the photon sphere, it is important to consider the implications it may have for future space exploration and our broader understanding of the universe. While the direct exploration of black holes and their photon spheres remains an elusive goal, advancements in both observational technology and theoretical models provide a glimpse of what might one day be achievable. One of the most exciting prospects on the horizon is the possibility of sending probes to study the environment near black holes, potentially providing unprecedented data on the behavior of light, matter, and time itself. Currently, the closest we can come to probing the space around a black hole is through indirect observations, such as the aforementioned gravitational lensing and the detection of high-energy radiation. These methods have provided invaluable information, but they are still limited by our inability to directly observe the regions inside the photon sphere. However, this may change as technology advances. With the development of more sophisticated space telescopes and other instruments, it may become possible to study the photon sphere more closely, even if it is still beyond our reach. In the future, space missions could be designed to approach the black hole's event horizon, allowing for more detailed measurements of the space surrounding it. These missions could involve sending specialized probes equipped with cutting-edge technology designed to withstand the extreme conditions near a black hole. These probes would be able to relay data back to Earth, offering a direct look at the environment inside the photon sphere and providing answers to some of the most profound questions in astrophysics. While this may sound like science fiction, there are already ongoing efforts to develop technology that could one day make such missions possible. For example, the concept of a gravitational wave observatory is being explored as a way to detect the ripples in spacetime caused by the movement of massive objects, including black holes. By observing these waves, scientists could gain valuable insights into the properties of black holes and the photon sphere. Moreover, the study of gravitational waves could also provide a way to test the limits of our current understanding of gravity and the nature of spacetime itself, particularly in the context of general relativity and quantum mechanics. In addition to the potential for space missions, the study of the photon sphere has far-reaching implications for other areas of physics. One of the most fascinating aspects of black holes and their photon spheres is how they challenge our understanding of fundamental physics. The intense gravitational forces near a black hole stretch and warp spacetime in ways that seem to defy the laws of physics as we know them. For example, time itself behaves in strange ways near a black hole, with time slowing down as you approach the event horizon. This phenomenon, known as time dilation, is a direct consequence of the warping of spacetime caused by gravity. Understanding the photon sphere, which exists just outside the event horizon, is crucial for understanding these strange time effects. The photon sphere represents a point where light is forced into a delicate balance between escaping and falling into the black hole. The behavior of light in this region is dictated by the curvature of spacetime, which in turn is influenced by the black hole's mass, spin, and charge. As such, studying the photon sphere provides valuable insights into how gravity behaves at its most extreme. Furthermore, the photon sphere also has implications for our understanding of quantum mechanics and its relationship to gravity. In recent years, physicists have made significant strides in developing a theory of quantum gravity, which seeks to combine the principles of quantum mechanics with those of general relativity. The photon sphere, with its extreme gravitational conditions, may provide a testing ground for this theory. By studying how light and matter behave in the region surrounding a black hole, scientists may be able to gain a deeper understanding of how quantum mechanics operates in the presence of strong gravitational fields. One of the most intriguing possibilities is that the photon sphere could help us unlock the mysteries of quantum entanglement. Quantum entanglement is a phenomenon where particles become linked in such a way that the state of one particle is instantly connected to the state of another, regardless of the distance between them. This strange phenomenon has been observed in laboratory experiments, but its true implications for our understanding of space and time are still not fully understood. Some theorists speculate that black holes, and by extension the photon sphere, could play a key role in unraveling the mysteries of entanglement and its relationship to the fabric of spacetime. Additionally, the study of the photon sphere has broader implications for our understanding of the structure of the universe itself. Black holes are often located at the centers of galaxies, and their influence extends far beyond the immediate vicinity of the event horizon. The massive gravitational pull of these objects can shape the structure of entire galaxies, affecting the motion of stars and the distribution of matter. In this way, understanding the photon sphere and the behavior of light near black holes can help us understand the larger cosmic picture and how galaxies and other cosmic structures evolve over time. The mysteries surrounding black holes and the photon sphere also raise important philosophical questions about the nature of existence and the limits of human knowledge. Black holes represent a boundary between the known and the unknown, a point where the laws of physics break down and our understanding of the universe is stretched to its limits. The photon sphere, with its bizarre properties and its connection to the most extreme environments in the cosmos, serves as a reminder of just how much we have yet to learn about the universe. As we look to the future, it is clear that the study of the photon sphere will continue to be a key focus of astrophysical research. With each new discovery, we move one step closer to understanding the fundamental nature of light, gravity, and the cosmos itself. The photon sphere may ultimately hold the key to some of the greatest mysteries of the universe, offering insights not only into the behavior of black holes but also into the very fabric of reality itself. In the coming years, as our observational tools become more advanced and our understanding of physics deepens, we may find that the photon sphere is not just a strange feature of black holes, but a gateway to understanding some of the most profound questions about the nature of space, time, and the universe. The study of the photon sphere is far from over, and as our knowledge continues to expand, we may one day uncover the full extent of its mysteries, revealing new insights into the workings of the cosmos. For now, the photon sphere remains one of the most intriguing and enigmatic features of the universe, a place where light and gravity are in a constant dance, shaping the very fabric of spacetime. As we continue to explore the farthest reaches of the universe, it is likely that the photon sphere will continue to captivate scientists and philosophers alike, challenging our understanding of the cosmos and inspiring new avenues of research into the fundamental nature of reality. The photon sphere represents one of the most captivating and complex regions of space, a place where light behaves in unexpected ways due to the extreme gravitational forces exerted by black holes. While we may not yet fully understand all the intricacies of the photon sphere, its study has already yielded invaluable insights into the nature of black holes, the structure of spacetime, and the behavior of light and matter in extreme conditions. As our observational capabilities continue to improve and our understanding of fundamental physics advances, the photon sphere may ultimately help us unlock some of the greatest mysteries of the universe. The journey to fully comprehend this strange and elusive region has only just begun, and the answers it holds may one day change our view of the cosmos forever. The photon sphere remains a key point of fascination for scientists and astronomers because of the unique way it challenges the fundamental laws of physics, especially the behavior of light and the nature of gravity. At the heart of this phenomenon lies one of the most fundamental forces in the universe, gravity. Black holes, particularly supermassive ones, are the ultimate expression of gravitational forces, bending and warping spacetime to an extent where light itself cannot escape. The photon sphere is a manifestation of this effect, showing us just how powerful gravity can be when it is concentrated in a small, dense region. As we continue to probe the mysteries of black holes, researchers also wonder about the potential impact the photon sphere might have on our understanding of the quantum world. Could the strange interactions between light and gravity near black holes reveal clues about how quantum mechanics and general relativity, two theories that currently operate in separate realms of physics, might one day be unified? The idea of a quantum theory of gravity is a major focus in theoretical physics. In this quest, the photon sphere plays a significant role by offering an environment where the effects of both quantum mechanics and general relativity could potentially overlap. By studying the behavior of light at the photon sphere, scientists may be able to observe how quantum processes operate in extreme gravitational fields, providing valuable data for the development of a more complete theory of physics. One possible consequence of this research is the discovery of new forms of matter or energy that behave differently in these intense gravitational fields. For instance, the interaction between light and the black hole's gravity might provide new insights into exotic matter or the elusive dark matter that makes up most of the universe's mass. Dark matter is one of the biggest mysteries in astrophysics today, and understanding how light behaves in environments like the photon sphere could help unravel some of these enigmatic questions. Moreover, the study of the photon sphere could also lead to a better understanding of the formation and evolution of black holes themselves. Black holes are thought to form when massive stars collapse under their own gravity, but the exact mechanisms behind their formation, especially the supermassive ones found at the centers of galaxies, remain uncertain. By observing the behavior of light near the photon sphere, scientists can gather important clues about the process by which black holes grow and how they might influence the surrounding space. These observations could also provide insights into how matter behaves under the extreme conditions near black holes, helping us understand what happens in the last moments before a star is consumed by a black hole, or when matter crosses the event horizon. Interestingly, the concept of the photon sphere has implications beyond black holes and may help answer some of the most profound questions in cosmology. For instance, it might contribute to our understanding of the expansion of the universe. Some cosmologists have hypothesized that black holes and the phenomena around them could offer insights into the overall structure of the universe. The photon sphere, in particular, might act as a natural laboratory for testing ideas related to the large-scale structure of the cosmos, helping us to understand how galaxies, stars, and other cosmic entities form and evolve over time. On a more speculative note, some scientists have even proposed that the photon sphere could offer a unique opportunity to explore the fabric of spacetime itself. As light bends and twists around a black hole, it traces the curvature of spacetime, creating a kind of cosmic map of the universe. By studying the patterns in which photons behave near the photon sphere, we might be able to learn more about how spacetime is structured on the largest scales and how it behaves in regions where the effects of gravity are at their most extreme. This could lead to a deeper understanding of the fundamental nature of the universe and perhaps even reveal hidden dimensions of space and time. Another intriguing aspect of the photon sphere lies in its connection to time. As light orbits a black hole in the photon sphere, time appears to slow down relative to an observer far away from the black hole. This effect, known as gravitational time dilation, is one of the most bizarre aspects of Einstein's theory of general relativity. It suggests that the closer an object is to a black hole, the slower time passes for that object. In the case of the photon sphere, this means that light traveling along this precarious orbit is subject to an extreme form of time dilation, which could have profound implications for our understanding of the passage of time in the universe. Understanding how time behaves in such extreme environments could help answer fundamental questions about the nature of time itself, and whether it is possible for time to behave differently in different parts of the universe. While all these possibilities are tantalizing, it is important to remember that studying the photon sphere is a monumental challenge. The conditions around black holes are so extreme that they push the boundaries of our current technology and understanding. Nevertheless, the increasing sophistication of our observational tools gives hope that one day, we might be able to observe these distant and mysterious regions more directly. For example, the Event Horizon Telescope, which captured the first ever image of a black hole in 2019, represents one of the most significant achievements in our ability to study black holes. Future advancements in this field could bring us closer to observing the photon sphere in action, allowing us to test theories about light, gravity, and spacetime in ways we never thought possible. In addition to these technological advancements, future theoretical work will likely play a key role in unlocking the full significance of the photon sphere. As our understanding of the universe deepens, we will develop new models and simulations that take into account the full complexity of black holes and the environments surrounding them. These simulations will help us understand how light behaves in the photon sphere and what this behavior can tell us about the nature of gravity, quantum mechanics, and the fundamental structure of the universe. The study of the photon sphere also has philosophical implications, particularly in relation to our place in the universe. Black holes are often seen as the ultimate cosmic mystery, and the photon sphere represents a boundary between the known and the unknown. Just as the event horizon marks the point beyond which nothing can escape a black hole, the photon sphere marks a point at which light itself can be trapped, forever caught in a dance between falling into the black hole and escaping into space. This creates a sense of mystery and awe, reminding us of how much we still have to learn about the cosmos and our place within it. The fascination with the photon sphere, then, is not only about the scientific questions it raises, but also about the philosophical and existential questions it prompts. What does it mean to observe a region of space where the normal laws of physics seem to break down? What can the study of these extreme environments teach us about the nature of reality itself? And perhaps most intriguingly, what secrets might the photon sphere hold that could forever alter our understanding of the universe? As our knowledge of black holes and the photon sphere continues to grow, it's clear that we are on the brink of discovering some of the most profound truths about the cosmos. Whether through advanced telescopes, theoretical models, or space missions, the future of photon sphere research holds immense potential. By pushing the boundaries of our understanding, we may one day uncover answers to some of the most fundamental questions in physics, time, and the universe itself. The photon sphere is one of the most intriguing and mysterious aspects of black holes, representing a region of space where light and gravity interact in a complex and often baffling way. While it remains an elusive and challenging subject of study, the photon sphere offers a wealth of possibilities for expanding our understanding of the universe. From its role in the behavior of light and gravity to its potential implications for quantum mechanics and time itself, the photon sphere stands as a testament to the complexity and wonder of the cosmos. As we continue to study and explore this strange and elusive region, we may one day unlock some of the greatest mysteries of the universe, transforming our understanding of space, time, and reality. The photon sphere is one of the most compelling and mind-bending phenomena in the universe, and as we've already explored, it holds great potential for expanding our understanding of astrophysics and cosmology. But even with the exploration we've done so far, there are still many facets of the photon sphere that warrant a deeper dive. For instance, the behavior of photons in the photon sphere, the possible observation techniques, and the further implications for the physics community are all subjects that could reveal even more mysteries. Let's first revisit the specifics of how light behaves in the photon sphere and why this region is so important for astronomers and physicists. Light, or photons, travels at an incredible speed, around 299,792 kilometers per second in a vacuum. However, when photons approach a black hole, they no longer travel along their usual straight-line paths. In fact, near the photon sphere, the gravitational pull is so intense that the trajectory of these photons can curve to such an extent that they end up orbiting the black hole. This orbiting behavior occurs at a specific radius around the black hole, which is at least 1.5 times the Schwarzschild radius, the radius of a non-rotating black hole's event horizon. What makes the photon sphere such an anomaly is that this behavior doesn't align with how we normally perceive the movement of light. In most situations, light moves in straight lines unless influenced by gravity or matter, but in the case of a black hole, gravity is so strong that it warps the spacetime fabric itself, bending the path of photons. The photon sphere is a direct result of this extreme warping, where light is forced into a delicate balance, one that, while theoretically stable, is still fragile. In fact, if anything disturbs this delicate equilibrium, the photons will either spiral inward toward the black hole's event horizon or escape into space. This is why the photon sphere, while fascinating, is inherently unstable and why photons don't generally remain in orbit for long periods of time. This instability brings us to an important point. Photons in the sphere don't stay there for eternity. They may orbit for a brief period, but eventually, they either fall into the black hole or escape into space. This fact underpins why the photon sphere is often considered a temporary phenomenon. The photons within it don't remain trapped in a perpetual orbit, and they don't create a permanent image of the black hole. This transitory nature of the photon sphere makes it difficult to directly observe, but scientists have been working diligently to come up with ways to capture and study the behavior of light around black holes, including the photon sphere. One of the key methods in which scientists have been able to observe phenomena related to the photon sphere is through the Event Horizon Telescope, EHT. The EHT made headlines in 2019 when it released the first ever image of a black hole's event horizon. While this image didn't directly capture the photon sphere, it gave us a glimpse into the incredible technology and techniques being developed to study black holes. The EHT captures data from a network of radio telescopes spread across the globe, essentially turning the planet into a giant telescope, allowing for unprecedented resolution. The data gathered from this network could, in the future, help scientists analyze the regions around black holes, including the photon sphere, to determine how light behaves and what physical laws govern this extreme region. While direct observation of the photon sphere remains a challenge, the growing capabilities of telescopes and the increasing power of computational models are allowing researchers to get closer to understanding it. High-resolution imaging, spectroscopic analysis, and more detailed simulations are expected to bring us ever closer to studying the photon sphere directly. This, in turn, will likely lead to greater insights into the dynamics of black holes and how they interact with their surroundings. But what exactly can we learn from studying the photon sphere? To answer that question, we need to consider some of the larger implications of the photon sphere in relation to the fundamental forces of nature, particularly gravity. The photon sphere offers an extreme environment where general relativity is tested to its limits. Because gravity is so strong near the black hole, scientists can use the photon sphere to probe how gravity behaves in such an intense region. This helps test and refine Einstein's general theory of relativity, which predicts how objects move in response to gravity. But the photon sphere does more than just test gravity. It also offers insight into the fabric of spacetime itself. According to general relativity, the curvature of spacetime is responsible for the gravitational effects we observe, and it becomes most pronounced in regions near massive objects like black holes. By studying the photon sphere, researchers can better understand how spacetime behaves when it is curved to such an extreme degree. What does this tell us about the overall structure of the universe? Can we learn about how the very fabric of the cosmos behaves under extreme conditions? Furthermore, the photon sphere is a region where the relationship between light and gravity becomes most apparent. Light is often thought of as something that travels in a straight line unless disturbed by matter. But in the photon sphere, gravity bends the path of light in such a way that it becomes trapped in orbit, creating an environment where light and gravity exist in a delicate dance. This interplay between light and gravity provides an opportunity to explore fundamental questions about the nature of both forces. Does this behavior of light indicate that there is still much we don't understand about the fundamental forces of nature? Could it provide clues to unify gravity with the quantum forces, which so far remain separate in our understanding of physics? Another avenue of research that the photon sphere presents is the study of the so-called information paradox. This paradox arises from the fact that, according to quantum mechanics, information cannot be destroyed. Yet, when something crosses the event horizon of a black hole, it seems to disappear forever. The study of light near the photon sphere may provide new insights into this issue, as it could help scientists figure out whether information is truly lost in black holes or if it is somehow preserved in some form. This is one of the key open questions in modern theoretical physics, and solving it could have profound implications for our understanding of the universe. Additionally, as we probe the photon sphere, it could yield new insights into exotic forms of matter and energy. For instance, researchers have long speculated that dark matter, an invisible substance that makes up a significant portion of the universe's mass, might behave differently under the extreme conditions found near black holes. Studying the photon sphere could give us a new way to probe dark matter by observing how light interacts with the region around a black hole. This could help astronomers detect the presence of dark matter and better understand its role in the formation and evolution of galaxies. Moreover, studying the photon sphere could also help shed light on the formation and growth of supermassive black holes. These black holes, which reside at the centers of most galaxies, are some of the largest and most mysterious objects in the universe. How do they form? How do they grow? The behavior of light near the photon sphere could help answer these questions by providing information about the processes that occur in the region surrounding these massive objects. By understanding the dynamics of the photon sphere, scientists could piece together a more complete picture of how supermassive black holes evolve over time. As we continue to learn more about the photon sphere, it may not only change the way we think about black holes but could also revolutionize our understanding of the universe as a whole. It is, after all, one of the most extreme environments we can study, offering us a glimpse into the universe's most bizarre and fundamental workings. Whether it's advancing our understanding of gravity, light, quantum mechanics, or dark matter, the photon sphere is a vital piece of the cosmic puzzle. The photon sphere represents one of the most mysterious and fascinating phenomena in astrophysics. It challenges our understanding of gravity, light, and space-time, offering a unique opportunity to study how these fundamental forces interact in extreme conditions. Although observing and studying the photon sphere is incredibly difficult, advancements in observational technology and theoretical physics are bringing us closer to understanding this bizarre and enigmatic region around black holes. By continuing to explore the photon sphere, scientists will not only unravel the mysteries of black holes but will also uncover deeper truths about the universe itself, pushing the boundaries of human knowledge in ways we never thought possible. The photon sphere is an integral concept for understanding the most extreme and enigmatic objects in the universe, black holes. As we venture further into the mysteries surrounding the photon sphere, it's crucial to recognize its place in the broader context of black hole physics. To fully grasp its implications, we must consider the impact of this phenomenon on our theories of gravity, light, and even the very structure of spacetime. At the heart of the discussion about the photon sphere is one of the most mind-boggling aspects of physics: the way spacetime is curved around black holes. In simple terms, spacetime is the fabric of the universe that governs how objects move, interact, and experience gravity. Einstein's general theory of relativity tells us that mass and energy warp spacetime, and the more massive an object, the more it curves the space around it. Black holes represent the ultimate extreme of this warping, so extreme that not even light can escape once it passes the event horizon. The photon sphere, being a few times outside the event horizon, is a crucial region where light can move in circular orbits under the influence of a black hole's powerful gravitational pull. But this region isn't just a scientific curiosity. It challenges our understanding of physics and spacetime itself. The photon sphere provides a natural laboratory for studying the bending of light, a phenomenon known as gravitational lensing. Gravitational lensing occurs when light passes through the curved spacetime around massive objects. It's a powerful tool in astronomy, allowing scientists to study distant galaxies, stars, and black holes. But the photon sphere offers an even more extreme example of gravitational lensing, showing us how light behaves in the intense gravity of a black hole's vicinity. At the photon sphere, photons aren't just bent in small amounts as they pass by massive objects like stars or galaxies. Instead, they are forced into a circular orbit around the black hole. These orbits, while theoretically stable, are precariously so. The slightest perturbation can cause the photon to either fall into the black hole or be flung away into space. The photon sphere is a chaotic, unstable region, but it's also a unique area for testing the nature of gravity, light, and even the very structure of spacetime. One of the key challenges for scientists in studying the photon sphere is the difficulty of observing this phenomenon directly. Black holes, by their very nature, are invisible to conventional telescopes. The region inside the event horizon, where no light can escape, is hidden from view. However, the space surrounding a black hole, including the photon sphere, can emit radiation and light. This radiation is emitted by the accretion disk, the hot, glowing matter that spirals toward the black hole before being devoured. The photons in this region of intense heat and pressure can be bent, distorted, and even trapped by the photon sphere. Scientists use this indirect observation to study the photon sphere. They measure the way light behaves as it passes near a black hole. For instance, the EHT, which captured the famous image of the black hole at the center of the M87 galaxy, used radio waves to study the light around the black hole. While this image didn't directly show the photon sphere, it did give scientists a glimpse into the intense gravitational environment surrounding the black hole. By analyzing how light is bent and distorted, scientists can infer the presence of the photon sphere and learn more about its structure and behavior. To take this a step further, we need to discuss what the photon sphere can tell us about the black hole itself. Understanding the photon sphere is not just a matter of studying light and gravity in isolation. It's about studying the fundamental properties of black holes. One of the biggest questions in modern physics is how the forces of gravity and quantum mechanics, two pillars of our understanding of the universe, fit together. Gravity governs the large-scale behavior of objects in the cosmos, such as stars, galaxies, and black holes, while quantum mechanics deals with the behavior of particles at the smallest scales. These two theories have yet to be reconciled, and black holes are seen as a natural place where these forces should meet. The photon sphere offers a unique window into this intersection of gravity and quantum mechanics. Because the photon sphere operates in a region where spacetime is highly warped and where light behaves in extreme ways, studying it could provide insights into how quantum effects may influence the fabric of spacetime at massive scales. For example, some physicists speculate that the behavior of photons near the photon sphere could reveal clues about the fundamental nature of black holes. Could this phenomenon help explain the mysterious behavior of matter and energy at the event horizon? Can it shed light on the so-called information paradox, which questions whether information is lost when it falls into a black hole? The potential answers to these questions are not just theoretical exercises. They could have profound implications for our understanding of the universe. By studying the photon sphere and its effects on light, gravity, and spacetime, we could unlock some of the deepest mysteries in physics, including the nature of dark matter and dark energy, the true behavior of black holes, and the potential unification of quantum mechanics and general relativity. One interesting possibility that arises from the study of the photon sphere is the potential for new astronomical phenomena. For instance, scientists have theorized that the photon sphere might produce unusual patterns in the way light behaves around black holes. These patterns could be observed using highly sensitive instruments, offering new insights into the environment around black holes. Furthermore, the photon sphere could play a key role in understanding the formation and behavior of exotic objects like wormholes, which are hypothetical passages through spacetime that could allow for faster-than-light travel or time travel. As we continue to develop more advanced observational tools, such as the James Webb Space Telescope and next-generation radio telescopes, we are likely to gain even more insight into the nature of the photon sphere. These technologies will allow us to study black holes and their surroundings in unprecedented detail, potentially revealing new phenomena that were once considered impossible to observe. This could lead to groundbreaking discoveries that challenge our current understanding of physics and open up new frontiers in our exploration of the universe. Moreover, the photon sphere could have applications beyond astrophysics. The understanding of how light behaves in such extreme conditions could have practical implications for fields like optics and communications. By studying the bending of light near black holes, scientists might develop new techniques for manipulating light in novel ways. These techniques could one day be used to create more efficient lasers, improve telecommunications, or even develop new technologies for space exploration. The photon sphere is not just a theoretical concept. It is a critical region of space that offers a wealth of opportunities for advancing our understanding of the universe. While direct observation remains a challenge, ongoing advancements in observational technology and theoretical models are pushing the boundaries of what we can learn. From providing insights into the nature of black holes to offering clues about the unification of gravity and quantum mechanics, the photon sphere is a vital piece of the cosmic puzzle. As we continue to study this fascinating phenomenon, we move one step closer to unlocking the secrets of the universe itself. As we continue our journey into the photon sphere and its potential ramifications, it's crucial to delve deeper into some of the most fascinating implications this phenomenon holds, not only for astrophysics, but for broader concepts in physics. The photon sphere is a place where our theories about the universe are stretched to their limits. It represents an area of space where light itself is subjected to the extreme warping of space-time. This, in turn, forces us to confront some of the most perplexing questions about the nature of gravity, light, and the fundamental structure of the cosmos. One of the most thought-provoking aspects of the photon sphere is its role in helping us understand the geometry of space-time around a black hole. The way light behaves in this region provides a direct manifestation of the curvature of space-time. In general relativity, gravity is not a force that acts at a distance, as we once thought in the Newtonian sense. Instead, it's the result of the curvature of space-time itself. The photon sphere, by trapping light in a circular orbit, provides a vivid illustration of this curvature. It's as if the fabric of space-time itself has become so warped by the black hole's immense gravitational pull that even light, which travels at the fastest speed in the universe, cannot break free without the right conditions. This idea challenges our intuitions and presents an opportunity to rethink how we understand the universe. In many ways, the photon sphere is like a cosmic funhouse mirror. Its gravity distorts everything that comes near it, bending light in ways we can't fully replicate here on Earth. While general relativity has provided us with a powerful framework for understanding how gravity works on large scales, the photon sphere serves as an intense testing ground for this theory. In fact, one of the primary ways scientists have tested general relativity is through observations of phenomena like gravitational lensing and the behavior of light around black holes. The photon sphere plays a central role in this, offering clues about how spacetime behaves in one of the most extreme environments in the universe. But the photon sphere is not just a theoretical concept. It also plays a practical role in our understanding of the observable universe. For astronomers, the behavior of light around black holes can offer a wealth of information about their properties. While we cannot directly observe the photon sphere itself, the effects it has on light provide us with an indirect view of the black hole's inner workings. For example, the phenomenon of gravitational time dilation, where time appears to slow down in strong gravitational fields, can be studied by observing the way light behaves near the photon sphere. This can help astronomers measure the black hole's mass, spin, and charge, as well as provide insights into the structure of spacetime around these mysterious objects. Moreover, the study of photon spheres can help refine our understanding of black holes' behavior in ways we never thought possible. Despite the advances in our understanding of these objects, much remains unknown about the true nature of black holes. For instance, the nature of the event horizon, the boundary beyond which nothing can escape a black hole's grasp, is still shrouded in mystery. Is the event horizon a smooth, well-defined boundary, or does it have some structure that could be observed through the behavior of light? The photon sphere could provide answers to such questions by offering insights into how light interacts with the black hole's boundary and how spacetime behaves near it. The photon sphere also raises intriguing questions about the relationship between light and gravity. In the context of black holes, photons are treated as massless particles. And yet, in the presence of intense gravitational fields, these massless particles are forced into circular orbits. This behavior suggests that the interaction between light and gravity is far more complex than our traditional understanding. It may indicate that, under extreme conditions, light behaves more like matter than we previously realized. This could lead to new ways of thinking about the fundamental nature of light, gravity, and their relationship. Another area where the photon sphere plays a crucial role is in the study of accretion disks. As matter falls toward a black hole, it forms a swirling disk of gas and dust known as the accretion disk. This material becomes heated to incredibly high temperatures as it spirals inward, emitting radiation in the process. The photon sphere is located just outside this region, and it influences the behavior of the radiation emitted by the accretion disk. Some of the photons produced in the accretion disk may get trapped in the photon sphere, only to be emitted again after being bent and distorted. This process can lead to the formation of unique light patterns that can be observed by astronomers. In fact, the study of the photon sphere and its interaction with the accretion disk could one day lead to breakthroughs in our understanding of black hole formation and growth. How do black holes accumulate matter? What role does the photon sphere play in regulating the flow of energy into these objects? These questions are still largely unanswered, but the photon sphere provides a unique vantage point from which to explore them. As we look to the future, the photon sphere will undoubtedly continue to be a focal point for astronomical research. The advent of more powerful telescopes and observational tools, such as the Event Horizon Telescope, EHT, and the James Webb Space Telescope, will allow us to peer deeper into the universe than ever before. With these advancements, we will be able to study the light coming from regions near the photon sphere in greater detail, offering new insights into the behavior of light, gravity, and spacetime. For instance, the EHT's groundbreaking image of the supermassive black hole in the center of the M87 galaxy showed us the shadow of a black hole, which is thought to be caused by the photon sphere. This was the first direct visual evidence of a black hole's existence, and it marked a major milestone in our understanding of these enigmatic objects. In the future, astronomers hope to capture even more detailed images of the regions surrounding black holes, focusing specifically on the photon sphere and the accretion disk. These images could help us refine our models of black holes and their behavior, providing insights into some of the most profound questions in physics. Beyond astronomy, the study of photon spheres could have practical applications in fields like quantum computing and telecommunications. While this may seem far removed from the study of black holes, there are unexpected parallels between the behavior of light around photon spheres and the way light behaves in other extreme environments. By studying how light is manipulated in the presence of strong gravitational fields, scientists could develop new techniques for controlling light in novel ways, which could lead to advances in technology. Ultimately, the photon sphere is a window into one of the most mysterious and extreme phenomena in the universe. It challenges our understanding of gravity, light, and spacetime, offering a unique perspective on the nature of black holes. As we continue to study these enigmatic objects, the photon sphere will remain a key focus of research, providing answers to questions that could transform our understanding of the universe and the laws that govern it. Whether it's through groundbreaking observations or theoretical advancements, the photon sphere will continue to shape our exploration of the cosmos for years to come. The more we explore the nature of the photon sphere, the more we come to realize just how much there is still to learn about the universe. It is within this region of intense gravity that some of the most bizarre, counterintuitive phenomena occur. Here, in the heart of the black hole's influence, light behaves in ways that challenge everything we thought we knew about how photons interact with gravity. The photon sphere exists at a distance from a black hole where the gravitational forces are so powerful that not even light can escape unless it is moving at the perfect speed and angle. In this zone, light itself becomes trapped by the curvature of spacetime. But here's where things get tricky. This isn't a simple black hole boundary where light is entirely swallowed up. Instead, in the photon sphere, light orbits in a precarious state, held in place by the gravitational forces pulling it inward. The concept of photons being trapped in circular orbits is a strange and fascinating one, because photons, as massless particles, should theoretically never stop moving. Yet, in the photon sphere, light gets caught in a loop, spinning around the black hole. These orbits are extremely unstable, though. A photon that strays just a tiny bit too far from its orbit will be pulled into the black hole, never to escape. On the other hand, if a photon is slightly off course in the other direction, it may escape the black hole's influence altogether. This delicate balance between being trapped and escaping is what makes the photon sphere such a unique and curious phenomenon. It's also important to note that this orbiting behavior happens not only at the photon sphere itself but can also influence the surrounding regions. The photons that are stuck in these orbits interact with other light traveling through the area, bending their paths in intricate ways. When we observe this, we see what's known as gravitational lensing, a phenomenon where light from distant stars and galaxies is bent around a black hole, giving us glimpses of the universe as it would appear if the gravitational forces weren't there. Gravitational lensing is one of the primary ways in which astronomers can detect black holes. The distortion of light caused by the gravitational field around a black hole often leads to visual anomalies in the form of multiple images, arcs, or even entire galaxies that appear magnified and stretched. This bending of light happens because photons from the distant background are deflected by the gravitational forces near the black hole. Essentially, the black hole acts as a massive cosmic magnifying lens. While the photon sphere is largely theoretical in its most detailed aspects, with our current understanding of physics, it's important to realize that such an environment exists at the heart of black holes. When astronomers study the photon sphere indirectly through gravitational lensing or the behavior of accretion disks, they are seeing the effects of light getting caught in the web of spacetime near the black hole. This indirect evidence provides the foundation for our understanding of photon spheres and their role in the larger context of black hole physics. One of the most intriguing aspects of studying black holes, particularly through the lens of photon spheres, is the insight it provides into the relationship between mass and spacetime. The more massive the black hole, the stronger the gravitational forces, and consequently, the closer the photon sphere is to the event horizon, the point beyond which no information can escape. For supermassive black holes, the photon sphere can exist at significant distances from the event horizon, on the order of several times the radius of the event horizon itself. This allows us to study black holes from a vantage point that lies just outside the point of no return. In these regions, light is still able to provide us with information, but it is extremely sensitive to the curvature of spacetime caused by the black hole. In addition to the theoretical and observational implications of the photon sphere, it raises fundamental questions about the nature of light itself. If light can be bent and trapped by a black hole's gravitational pull, does this suggest that gravity can influence the very nature of photons? Could this mean that light behaves differently in extreme gravitational fields compared to weaker ones? We already know that light behaves as both a wave and a particle, depending on how we observe it. Does the photon sphere represent another manifestation of this dual nature of light, where photons are caught in an endless loop of orbital motion due to gravity, instead of moving along a straight line as they do under more conventional conditions? The photon sphere, while still somewhat theoretical in nature, also plays a significant role in our broader understanding of space-time. The very concept of gravitational lensing has profound consequences for how we view the universe. For example, when light from a distant star passes near a black hole, it can bend in such a way that it seems as if the light is coming from an entirely different direction. This can distort the image of the star and even cause multiple copies of the same star to appear in our sky, depending on the angle of the light's path relative to the black hole. These effects, while subtle, open up entirely new possibilities for how we observe and interpret the cosmos. The photon sphere also contributes to our understanding of the extreme conditions at the center of galaxies. In the case of supermassive black holes, which are believed to reside at the centers of most galaxies, the region surrounding the photon sphere is often filled with highly energetic radiation from the accretion disk. This radiation can provide us with valuable clues about the behavior of matter and energy under the influence of one of the most powerful forces in the universe. Observing this radiation can also help us understand the processes that lead to the formation and growth of black holes, as well as the broader evolution of galaxies themselves. Moreover, the potential discoveries surrounding photon spheres are far from over. With advancements in observational technology, we're now able to study black holes and the surrounding regions with more detail than ever before. Telescopes like the Event Horizon Telescope, EHT, have already made headlines for capturing the first-ever image of a black hole's event horizon, and astronomers are eagerly looking to capture even more detailed images in the future. This will allow us to study the photon sphere's role in greater depth and refine our models of how black holes interact with their surroundings. As technology progresses, the chances of unraveling the mysteries of the photon sphere and its impact on the universe will only increase. In addition to its importance in astrophysics, the photon sphere has broader implications for our understanding of fundamental physics. It's a key piece in the puzzle of general relativity and quantum mechanics, both of which are still, to some extent, separate frameworks for understanding the universe. While general relativity describes gravity on large scales, it struggles to account for quantum phenomena, like the behavior of light at the photon sphere. If we can unlock the secrets of the photon sphere, we may find a way to bridge these two theories and create a unified theory of quantum gravity. This would be a monumental step forward in our understanding of the universe, allowing us to reconcile the forces of the very large and the very small in a way that we have been unable to do thus far. The photon sphere, in its elegance and complexity, serves as a reminder of how much there is yet to explore in the universe. It's a place where light behaves in ways we cannot fully predict, a place where the laws of physics are pushed to their very limits. As we continue to explore this and other mysteries of the cosmos, we gain a deeper understanding of the forces that shape our universe, from the largest galaxies to the smallest particles. The more we uncover about the photon sphere, the more we realize that the universe is far more mysterious and awe-inspiring than we could have ever imagined. And as we push forward into the uncharted territories of space, one thing is certain: the photon sphere will remain one of the most compelling and enigmatic regions in the study of black holes and the universe at large. The mysteries of the photon sphere continue to shape our understanding of space, light, and gravity, making it one of the most fascinating aspects of black hole physics. But even as we uncover more details about how light interacts with black holes in this region, there are still fundamental questions that remain unanswered. For instance, how does the photon sphere influence the behavior of light in the far-reaching space around it? What role do quantum effects play in shaping the light trajectories as they orbit in this precarious balance? These questions are not just academic. They have profound implications for our understanding of the universe. Every discovery we make about black holes and the photon sphere can lead to broader insights about the nature of spacetime itself. For instance, we know that the intense gravitational fields of black holes cause massive warping of spacetime, affecting not only light but also time itself. In the vicinity of the photon sphere, time behaves differently compared to what we experience in less extreme environments. This effect, known as time dilation, is predicted by Einstein's theory of general relativity. The closer one gets to the photon sphere, the more pronounced the time dilation becomes, eventually reaching a point where time seems to stop completely at the event horizon. This peculiar phenomenon also brings us back to the question of whether we can ever truly understand black holes. While we can observe their effects on surrounding matter and light, we cannot directly observe what happens within the event horizon or inside the photon sphere itself. No matter how advanced our technology becomes, we may never fully unlock the secrets hidden within these regions, since nothing, not even light, can escape their grip. The photon sphere remains as much a symbol of the unknown as it is a tangible feature of the cosmos. Another layer of complexity lies in the fact that the photon sphere is not unique to black holes. While it is most commonly associated with these gravitational behemoths, similar phenomena can occur around other objects with extremely strong gravitational fields, such as neutron stars or even certain types of white dwarfs. These objects may not have the same capacity to trap light in stable orbits as black holes, but the same principles apply. Light gets bent and caught by the intense curvature of spacetime. The difference is that the photon sphere around black holes is much more pronounced and can extend much closer to the object itself, whereas in other cases, the photon sphere is much farther away and less stable. As we push the boundaries of our observational tools, scientists are beginning to probe these mysterious regions more deeply. Advanced instruments like the Event Horizon Telescope, EHT, which captured the first ever image of a black hole's shadow in 2019, are providing astronomers with unprecedented views of the environments around supermassive black holes. The EHT team's work has opened up new possibilities for studying the photon sphere. With higher-resolution images and more detailed observations, we can now map the contours of the photon sphere and observe the intricate interplay between light and gravity in ways that were once unimaginable. This opens up an exciting frontier in astrophysics, where we can directly test the predictions of general relativity and see how light behaves in the most extreme conditions. Through these observations, we can better understand how gravity shapes not just matter but also energy, and how spacetime bends and stretches in response to the presence of massive objects like black holes. The photon sphere is like a cosmic laboratory where the laws of physics are stretched to their limits, giving us a unique opportunity to explore the very fabric of the universe. At the same time, these advances in observational technology are also driving forward theoretical research. As we continue to observe the behavior of light near black holes and neutron stars, theorists are refining their models of how photons interact with intense gravitational fields. There are still many unanswered questions about the stability of photon orbits in the photon sphere, especially in extreme conditions like those found near rotating or charged black holes. Theoretical work continues to challenge our understanding of these systems, raising new questions and providing fresh perspectives on what may be happening at the very edges of spacetime. Additionally, the photon sphere is not just a curiosity for astrophysicists. It is also becoming increasingly relevant in the search for gravitational waves. These ripples in spacetime, caused by the collision and merging of massive objects like black holes, are another exciting frontier in astrophysics. As we detect and study gravitational waves, we are starting to learn more about the environments around black holes, including their photon spheres. This new dimension of research could offer even more insight into the nature of light and gravity, as well as the behavior of matter in extreme environments. With all this in mind, the photon sphere becomes more than just a theoretical construct. It's a key piece of the puzzle in our quest to understand black holes, gravity, and the very nature of spacetime. It represents the threshold of light's struggle against the relentless pull of a black hole's gravity. It's a place where light can exist in delicate orbits, but only for a fleeting moment, as it battles to escape the gravitational grip of the singularity at the black hole's heart. In the grand scheme of the universe, the photon sphere is an essential feature of black holes, one that offers us a window into the workings of the cosmos on the most fundamental level. It allows us to observe the strange, complex interactions between light and gravity, and provides a testing ground for our most advanced theories of physics. And as we continue to explore the mysteries of black holes, the photon sphere will undoubtedly remain one of the most captivating phenomena to study. Ultimately, the photon sphere challenges our understanding of the universe, forcing us to confront the limits of our knowledge and our imagination. It pushes the boundaries of what we can observe, understand, and predict. And in doing so, It reminds us just how much there is still to discover in the vast, mysterious cosmos we call home. As science progresses and technology advances, we may one day uncover even more about the photon sphere and its role in shaping the fabric of spacetime. But for now, it stands as one of the many mind-bending mysteries that continue to intrigue and inspire those who dare to seek the answers to the most profound questions of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.